In the beginning, there was no stillness. The universe was never born from silence, but from motion. Galaxies are not frozen sculptures suspended in emptiness. They are whirlpools in an invisible ocean, spinning, merging, colliding, their arms stretched across billions of light years like waves cresting upon a boundless sea. Between those spirals, space-time itself bends and flexes, rippling with the passage of mass and energy. The fabric of the cosmos is not solid nor static. It flows. Imagine standing at the edge of that great expanse, if such an edge could exist. You would not see the universe expanding like dots on a balloon, but rather you would feel it moving, surging, as if every galaxy were caught in a current of unseen water. Gravity, the force that binds all of this together, is not merely a pull. It is a movement, a flow beneath reality, a tide in the deep ocean of space-time. Einstein taught us that space and time are not separate things. They are woven into a single, dynamic fabric. When mass and energy move through it, they cause it to curve. Planets orbit stars not because they are pulled by invisible strings, but because the geometry of space-time guides them along curved paths. In this picture, gravity is geometry. It is the curvature of the universe responding to the presence of matter. But even Einstein's equations, beautiful as they are, describe a universe that bends but does not flow. The mathematics of general relativity gives us a map of how space-time curves, yet it does not tell us what space-time is made of. It describes its shape, not its substance. If we look closer, at scales far smaller than atoms, a strange question arises. What if space-time is not fundamental? What if it is an emergent phenomenon, like the surface of a river that seems smooth from afar, yet beneath it, countless molecules dance in constant motion? Could gravity be the large-scale behavior of some deeper quantum fluid, an invisible sea whose ripples we call curvature? To answer that, we must first understand what it means for something to flow. In a river, flow is not only movement, but the redistribution of energy. Molecules of water interact, exchanging momentum, generating waves and eddies. In fluids, geometry and motion are intertwined. When a fluid moves faster in one region and slower in another, pressure differences appear. Those differences shape the flow, guiding it, balancing it, creating stability or turbulence. The mathematics that governs fluids, equations of continuity, of pressure, of energy conservation, describes how motion sustains itself. Now imagine replacing the molecules of water with the quanta of space-time itself. The ripples of that fluid would not be made of matter or light. They would be distortions in the metric of reality. Gravitational waves, those faint tremors detected by LIGO when black holes merge, are precisely such ripples. When two black holes spiral together, they disturb the fabric of space-time, sending waves traveling across the cosmos. These waves do not fade quickly. They journey for billions of years without losing strength, without friction, without decay, as if the universe were a perfect fluid, flowing without resistance. Physicists began to notice this parallel. The way gravity propagates, the way waves in space-time move, follows equations eerily similar to those used to describe the flow of fluids. Even Einstein's field equations can be rewritten to look like the equations of fluid motion. Pressure becomes curvature. Flow becomes change in geometry. Space behaves, in a sense, like a fluid in motion. So perhaps gravity is not simply the bending of space. Perhaps it is the movement of something deeper, a flow so subtle that we can only see its surface. The universe, then, is not a static structure, but a living system, continuously evolving, flowing, exchanging energy across scales. Black holes may be whirlpools in that cosmic fluid, regions where the flow becomes so intense that not even light can escape. And yet, the deeper we dive, the stranger the water becomes. Near the event horizon of a black hole, where curvature grows without limit, classical physics begins to fail. Space stretches, time dilates, and the equations of relativity lose their meaning. It is here that quantum theory must take over, for at such extremes, space-time itself may begin to reveal its molecular structure. This is where scientists first began to wonder whether gravity might behave like a fluid, not metaphorically, but literally. The hints came from black hole physics, where ideas about temperature, entropy, and information began to merge with geometry. Black holes radiate energy, a phenomenon known as Hawking radiation, suggesting that they possess temperature and entropy. These are thermodynamic properties, the same language we use to describe gases and liquids. So how could a purely geometric object, a region of warped spacetime, behave as if it were a hot body emitting particles? The answer, though still mysterious, suggests that the fabric of spacetime is not smooth but granular, with microscopic degrees of freedom, just like a fluid composed of molecules. When those degrees of freedom rearrange, they create curvature, motion, and flow, what we perceive as gravity. The cosmos, then, might be less like a static stage and more like a living ocean, an unending current through which matter, energy, and information drift endlessly. What we call emptiness is anything but empty. It is filled with motion, fluctuations, and quantum fields that never rest. The vacuum of space hums with virtual particles appearing and disappearing faster than the blink of an eye. Even in perfect darkness, the sea of space-time never stands still. It moves, it flows, it breathes. As galaxies rotate, as stars ignite and die, as black holes merge, they send ripples through this medium. Those ripples are gravity's voice, a whisper from the deep. And if we listen carefully enough, perhaps we can hear the current that carries the universe forward, a silent river beneath all things, shaping every orbit, every fall, every rise. The deeper we study the heavens, the more this idea of a flowing space-time begins to feel real. Astronomers observing colliding galaxies see waves of distortion sweeping through the cosmic web, bending light and stretching time itself. These distortions travel through the vacuum as if through a medium, yet relativity tells us there is no medium. Space is supposed to be nothing, only geometry. And yet, the way these waves behave defies the intuition of nothingness. They refract, they interfere, they carry energy from one side of the universe to another without ever dispersing. That persistence hints at something perfect, something continuous, something that flows without friction. The ancient idea of an ether once tried to explain this, but Einstein banished the ether, declaring that light and gravity need no medium. Still, over a century later, the equations whisper a contradiction. The vacuum behaves as if it were something after all. Not a rigid structure, but a kind of fluid field. One that flexes and flows in ways too subtle for ordinary matter to detect. If you could zoom in on a single cubic centimeter of space and see its quantum fabric, it would shimmer like the surface of a lake under starlight, vibrating with fluctuations at scales of 10 to the power of -35 meters. At those scales, space-time becomes restless. Virtual particles flash in and out of existence. Energy surges and collapses in fleeting patterns, and geometry itself quivers. To an observer large enough, this dance averages out into smoothness, the same way the molecules of air feel like a continuous wind on your skin. But the truth beneath is more turbulent. It is motion all the way down. General relativity describes how that motion appears on the grand scale, when the flow becomes slow and steady. Massive objects create depressions in the fabric, and other objects follow the curves of that flow. It is elegant, continuous, deterministic. But quantum field theory looks at the same stage and sees a storm. Gravity is not a static bend, but a wave pattern forming and dissolving at unimaginable speeds. These two views, the smooth and the turbulent, are not opposites. They are different resolutions of the same reality. The universe can be both a river and a storm, depending on how closely you look. This understanding leads physicists to a breathtaking thought. What if the geometry of space-time is not the starting point, but the consequence. What if the flow we call gravity arises from microscopic interactions among hidden quantum constituents, much as the flow of water arises from the collisions of countless molecules? In that case, Einstein's equations are not the deepest truth, but the hydrodynamic limit of something even more fundamental. They describe how the large-scale flow behaves, not what creates it. To grasp this, we can turn to fluids we understand. When you study a droplet of water, you do not see the molecules themselves, only their collective motion. The mathematics that describes the wave of the droplet, its ripples, and its surface tension does not depend on the details of each molecule. The behavior emerges from the collective. In the same way, the smooth curves of spacetime could emerge from countless microscopic quanta of geometry, entities that obey quantum laws, but together appear continuous and fluid. Einstein's relativity, then, is the hydrodynamics of spacetime. It tells us how the flow evolves, how it bends and stretches under energy and mass, but it does not reveal what flows. That mystery belongs to quantum gravity, a theory not yet fully written, but hinted at in the patterns of the cosmos. When we observe a gravitational wave traveling across billions of light years, we are watching the surface motion of that deeper medium. It carries information about its source, two black holes locked in a dance of destruction. Yet it also reveals something about the fluid itself. The fact that these waves arrive unchanged, undamped, after eons of travel, tells us that spacetime has no viscosity. It does not resist motion. It is the perfect superfluid, capable of transmitting ripples without loss. In laboratories on Earth, scientists have begun to mimic this behavior using analog systems. They create horizons inside flowing fluids, where sound waves cannot escape, sonic black holes. In these experiments, the mathematics describing sound waves in moving fluids mirrors exactly the equations of light and gravity near a real black hole. The analog fluid develops its own form of Hawking radiation, a thermal emission from the horizon. This is not an illusion, it is a window. It shows us that the geometry of spacetime and the behavior of a flowing fluid can be described by the same underlying structure. The insight is profound. It means that what we call curvature, the bending of spacetime, may be only the macroscopic appearance of motion in a deeper field. A flow of information, energy, or quantum states that together create the illusion of gravity. The universe may not merely contain fluids, it may be one. Every ripple of gravity, every distortion of time, could be the echo of motion in that invisible ocean. If so, then black holes are no longer just regions of collapsed geometry. They are vortices, whirlpools in the cosmic flow. The event horizon marks the boundary where the current becomes so strong that not even light can swim against it. Matter does not vanish there. It becomes part of the circulation, its energy and information drawn into the deeper currents of spacetime itself. To think of gravity this way changes everything. It transforms our understanding of what the cosmos is made of. Space and time are no longer passive containers, but active participants, elements of a vast and continuous medium. The stars drift not through emptiness, but through an invisible substance more fundamental than any particle. This substance cannot be touched or seen, but its movement shapes every orbit, every wave, every heartbeat of the universe. And just as water shapes the stones of a riverbed, the flow of spacetime sculpts reality. It carves galaxies, draws filaments of dark matter, sets planets into motion, and determines the rhythm of cosmic evolution. The same laws that guide rivers and winds may echo on unimaginable scales through the physics of the cosmos itself. So the question remains, if spacetime behaves like a fluid, what kind of fluid is it? Does it have temperature, viscosity, entropy? Can it flow faster or slower, form vortices, or even freeze into a quantum condensate? These are not poetic metaphors, but active questions at the frontier of physics. The first hints lie not in the stars, but in the mathematics, and in the laboratory, where scientists try to make space behave like water. From this point, we descend into the quantum depths, where experiments in superfluid helium and Bose-Einstein condensates reveal the same mathematics that governs black holes and expanding space. In those frigid, shimmering droplets, physicists see the behavior of the cosmos itself. A mirror in miniature, whispering that perhaps the universe flows in ways we are only beginning to imagine. At the deepest level, the idea of a flowing universe reshapes how we imagine reality itself. For most of human history, space was thought to be the backdrop, the unmoving stage on which matter performed its dance. Then came Einstein, and the stage came alive. Space could stretch, twist, and ripple. But now, in this new vision, even Einstein's living stage may be an illusion, the visible surface of something deeper and more dynamic, a current that never ceases to move beneath the skin of existence. Consider how the cosmos behaves. The expansion of the universe is not the spreading of objects through space, but the stretching of space itself. That stretching can be described as flow. In the first fraction of a second after the Big Bang, the infant universe expanded faster than light, not because things moved through space, but because the fabric of space-time itself surged outward, carrying everything within it, like debris caught in a great tide. The cosmic microwave background, the faint afterglow of that early expansion, is the fossil wave pattern of that primordial flow. If we treat this expansion as a flow, the question becomes not why the universe expands, but what drives the current. What pushes the cosmic ocean to keep stretching? The answer may lie in the energy density of the vacuum itself, the so-called dark energy. Though invisible, it exerts a pressure, like the pressure in a fluid, driving the universe to accelerate. This is not metaphoric language, it is literal. The cosmological constant in Einstein's equations behaves exactly like a uniform pressure filling space, a steady flow of energy that sustains the expansion. Everywhere we look, we find echoes of fluid behavior. Galaxies form filaments like tendrils in turbulent flow. Black holes spin like whirlpools. The cosmic web resembles the foam of bubbles in a liquid, its voids and clusters forming patterns that could be mistaken for the structures of a boiling fluid. Even time itself may have a current. We feel it as a one-way motion, from past to future, as if caught in an irreversible stream. Thermodynamics tells us that this arrow of time emerges from entropy, from the tendency of systems to flow toward equilibrium. Once again, flow defines the story. But if space flows, it must have rules. And in the universe, those rules are written by mathematics. The Einstein field equations are like the Navier-Stokes equations of the cosmos, describing how energy and momentum curve the geometry, how curvature evolves, and how waves propagate through the medium. In this sense, general relativity is not just a theory of gravity, it is a theory of flow. The curvature of space-time corresponds to the gradients of energy, just as pressure gradients drive the movement of fluids. When energy shifts from one region to another, space-time responds, reshaping itself to maintain balance. Yet every flow has limits, boundaries where our understanding breaks down. At the heart of black holes, the current becomes infinite. The equations of relativity predict a singularity, a point where curvature grows without bound. But no real fluid behaves this way. In physical systems, infinite densities are signs that the theory describing them has reached its edge. Beyond that edge lies new physics, quantum gravity. The flow of gravity, if it exists, must continue smoothly past where relativity fails. Inside that mystery may dwell the true quantum nature of space-time, where geometry dissolves into information and flow becomes computation. Some physicists believe that space-time emerges from networks of quantum entanglement, a vast web of relationships between particles that collectively form the geometry we perceive. In that picture, flow is not of matter or energy, but of information itself. Entanglement weaves the fabric, and the redistribution of that entanglement creates the motion we interpret as gravity. If this is correct, the universe is both digital and fluid. Its quantum bits form the atoms of spacetime, while their collective motion creates the analog wave of geometry. The smallest fluctuations give rise to the largest structures. Quantum foam at the Planck scale swells into galaxies and clusters, just as microscopic water molecules produce the surge of an ocean tide. The boundaries between the microscopic and the cosmic dissolve into a single continuum of flow. And in this continuum, we find a new kind of beauty, one that connects the mathematics of fluids with the poetry of existence. Imagine space-time not as an empty void, but as a vast and shimmering current. The stars drift through it as leaves upon water. Planets trace their orbits as eddies around greater masses. Every fall, every orbit, every gravitational wave is part of a grand choreography that began 14 billion years ago and continues still. When we detect a gravitational wave passing through Earth, we are touching that current. The mirrors of the detectors tremble ever so slightly as the wave flows through them, changing the distance between them by less than a fraction of the width of a proton. Yet in that trembling, we can feel the pulse of the universe itself. It is the same pulse that shaped the first galaxies, the same flow that carved the fabric of time. There is something humbling in that realization. We are not outside observers looking at a cosmic ocean from a distance. We are within it. Every atom in our bodies, every heartbeat, every thought takes place within that same current. We are patterns in the flow, temporary formations in the great river of space-time. And as we move through it, we sense the same mystery that has guided science for centuries. What is the nature of the flow that binds the universe together? Is gravity a field, a curvature, or a current of something deeper still? The answer may lie in the bridge between relativity and quantum mechanics, where geometry becomes thermodynamics and information becomes energy. The first hints of this unification appeared in the study of black holes, where the mathematics of temperature, entropy, and flow emerged unexpectedly from pure geometry. It was there, in the physics of horizons, that scientists first glimpsed the truth. Space-time may not only bend, it may behave like a fluid in equilibrium, governed by the same principles that rule the flow of heat and the motion of gases. And so, the story of gravity leads us from the vastness of galaxies to the quiet hum of thermal radiation, from cosmic currents to microscopic vibrations. The universe, it seems, is one continuous flow, from the largest scales to the smallest. In the chapters that follow, we will dive deeper into this idea. We will see how experiments with superfluids and Bose-Einstein condensates mimic the behavior of space-time, how the mathematics of acoustic horizons mirrors that of black holes, and how the very vacuum of the universe may behave like a quantum liquid at absolute zero. We will explore how entropy, temperature, and information come together to reveal gravity as a flow, not of matter, but of reality itself. Perhaps, in the end, we will discover that gravity does not pull at all. It flows, and we, suspended in its current, are carried through the endless tides of space-time, drifting with the rhythm of the universe. In the stillness of a laboratory, far removed from the stars, physicists have learned to make space itself come alive. They cannot yet bend space-time as gravity does, but they can make matter behave in ways that echo its flow. When light, sound, or even atoms move through these artificial systems, they imitate the laws of the cosmos. What unfolds on the tabletop begins to resemble what happens at the edges of black holes or in the earliest moments after the birth of the universe. It begins with fluids, with supercooled liquids, whispering gases, and the faint shimmer of quantum condensates. When certain substances are chilled to near absolute zero, their particles lose their individuality. They begin to act as one, their quantum waves merging into a single collective rhythm. This is the Bose-Einstein condensate, a state of matter where quantum mechanics leaps from the microscopic into the macroscopic world. Within this delicate frozen material, sound moves differently. It travels as if through curved space-time. Decades ago, the physicist William Unruh proposed a bold idea. He imagined a river of fluid flowing faster and faster until, at a certain point, its speed exceeded the speed at which sound could travel upstream. Beyond that point, no sound wave could escape, just as nothing can escape a black hole once it passes the event horizon. This was the birth of the concept of an acoustic black hole, a sonic horizon created not by gravity, but by motion. The mathematics describing this phenomenon matched, line for line, the equations of general relativity. To most, it sounded like an elegant analogy, but to those who looked deeper, it was something more. It suggested that the geometry of space-time and the behavior of flowing fluids were not merely similar. They might be expressions of the same underlying principle. If the equations were identical, then perhaps nature itself was telling us that gravity is not unique. It is one face of a deeper symmetry between motion, energy, and flow. Years later, this idea left the realm of theory and entered experiment. In the 2010s, physicist Jeff Steinhauer and his team created an actual sonic black hole in a Bose-Einstein condensate. They cooled a cloud of rubidium atoms to near absolute zero and set it flowing faster than the speed of sound within itself. Then they listened, and they heard something extraordinary. A faint whisper of phonons, sound particles, emitted from the horizon of the fluid, just as Stephen Hawking had predicted black holes should emit radiation. This was not metaphorical. It was real, measurable, physical. Hawking radiation, long thought impossible to detect from actual black holes because of its weakness, had finally been observed in the laboratory, not from gravity, but from fluid flow. The implication was staggering. If a fluid could mimic a black hole, and if its behavior produced the same radiation, then the physics of space-time might truly be fluid-like at its core. In these analog systems, scientists discovered that waves do not care about what the medium is made of. They care only about how it moves. Whether it is a fluid of atoms, a field of light, or the geometry of space-time itself, the waves respond to the same mathematical structure, something called the acoustic metric. This metric describes how motion shapes the propagation of waves. It defines horizons, curvatures, and flows. In relativity, the metric is what defines gravity. In a fluid, the flow defines the acoustic metric. The two are reflections of one another, so when space behaves like a fluid, the laws of physics echo the same symphony, only transposed into a different key. The ripples of gravity become sound waves. The curvature of space-time becomes a pressure field. The expansion of the universe becomes the outward rush of a flow. Every pattern we see in the heavens, every ripple of gravitational radiation, every inflationary burst of expansion, finds its counterpart in the laboratory, within a few centimeters of quantum liquid. This connection has given rise to an entirely new field known as analog gravity. Its experiments have not only deepened our understanding of black holes, but have reshaped how we think about the cosmos itself. They remind us that the universe is not built from static blocks of geometry, but from relationships, from flows and interactions that echo across scales. The same mathematics governs the fall of sound in a condensate and the fall of light into a black hole. It is as though nature has one language, written in the equations of flow, and everything, from the smallest droplet to the largest galaxy, speaks it. When we observe a wave traveling through a fluid, we are, in a sense, witnessing a miniature version of space-time itself at play. The geometry that bends around stars may not be so different from the ripples that spread across a pond, yet the deeper question remains: is this similarity only coincidence, or is it telling us something fundamental? Could it be that space-time itself is a fluid? That what we call curvature is the macroscopic effect of motion in an unseen quantum medium? To imagine this, think of the universe as a superfluid, a substance that flows without resistance, without loss, without heat. In a superfluid, motion persists forever. There is no friction, no viscosity. Once set in motion, it glides endlessly. Gravity behaves this way too. The gravitational waves that traverse the cosmos do not fade as sound does in air. They travel without dissipation, without energy loss, as if moving through a perfect medium. If space-time were such a superfluid, its behavior would naturally explain why gravity is so smooth, why its waves can cross billions of light years unchanged, and why its geometry can stretch without tearing. It would also suggest that beneath the smooth continuum of space and time lies a quantum condensate, a field made of countless microscopic quanta that move together in perfect unity. In that picture, the universe becomes a single vast droplet of superfluid, cooled to near absolute zero, humming with quantum motion. The flow of this superfluid gives rise to gravity, to inertia, and perhaps even to the expansion of the cosmos. Black holes are not singularities, but vortices, stable, rotating structures within the flow. Their horizons are not edges, but boundaries where the fluid's speed reaches a critical point. This vision transforms our understanding of everything. It unites the cold precision of quantum mechanics with the sweeping motion of general relativity. It tells us that the universe may be simple after all, a single, self-organizing fluid whose flow gives rise to the appearance of space, time, and gravity. But before we can accept such a vision, we must test it. We must see whether the mathematics of fluids can truly give rise to Einstein's equations, whether the flow of a condensate can reproduce the exact curvature of spacetime. To do that, physicists began to study the acoustic metric in detail, tracing how it governs waves in both sound and gravity. And what they found was astonishing. The same mathematics that describes how pressure and velocity shape the propagation of sound in a moving fluid can be rewritten to describe how mass and energy shape spacetime itself. The flow of the fluid defines an effective geometry, complete with horizons, curvature, and even gravitational lensing. Space behaves like a fluid because, in every measurable sense, it follows the same rules. In the quiet chambers of these laboratories, the hum of pumps and lasers becomes the heartbeat of an artificial cosmos. Within a small glass chamber, a cloud of atoms floats, held in place by magnetic fields, and cooled until motion itself seems to stop. Yet beneath that stillness, something extraordinary happens. The atoms begin to move as one. They no longer behave as separate particles, but as a single quantum entity, a coherent wave of matter. In this unity, scientists glimpse a reflection of the universe itself, a system that, on its deepest level, may also move as one. When physicists send a sound wave through such a condensate, the wave does not merely travel through space, it shapes space. The density and velocity of the fluid define an effective geometry, one that can bend and stretch as the flow changes. If the fluid moves faster in one region and slower in another, the sound waves curve, trapped by the geometry just as light is trapped by a gravitational field. The mathematics of this phenomenon is exact. It is not analogy, but equivalence. The equations that govern the curvature of spacetime also govern the behavior of the fluid's flow. This is the acoustic metric, a concept that has become one of the most beautiful bridges between general relativity and quantum mechanics. It shows that geometry can emerge from motion, that curvature can be generated by flow. In the laboratory, when the velocity of the condensate reaches a certain threshold, it forms a horizon. Sound waves cannot escape beyond that boundary. They fall inward, carried by the current, forever trapped, a perfect mirror of a black hole's event horizon. What happens at that horizon is one of the most mysterious processes in all of physics. Stephen Hawking discovered that black holes, despite their name, are not completely black. They emit a faint radiation, born from the fluctuations of quantum fields near the horizon. Pairs of virtual particles appear and annihilate constantly in empty space. Near a black hole, One particle falls in while the other escapes, carrying away energy as real radiation. Over immense timescales, this process causes the black hole to evaporate. For decades, this prediction stood untested. Real black holes are too distant and too cold to reveal their faint glow. But in the laboratory, using the language of fluids, scientists found a way to bring this effect to life. In the flowing condensate, quantum fluctuations create pairs of sound particles, phonons, near the acoustic horizon. One falls inward, while the other escapes, producing a measurable signal. This was the first time the Hawking process had been observed not as a mathematical concept, but as an experimental fact. It is a profound revelation. The same equations describe both sound in a fluid and light near a black hole. The same patterns appear whether the medium is water, air, or spacetime itself. This means the essence of gravity, the way it shapes and transmits waves, is not unique to geometry. It is a universal behavior of systems in motion. Physicists now realize that relativity and fluid dynamics may be two sides of the same coin. In both, what matters is how energy moves, not what it is made of. A fluid flows according to pressure and density gradients. Spacetime curves according to energy and momentum. Both obey conservation laws that express the same truth. Motion seeks balance, and imbalance creates motion. In this way, the universe maintains its own equilibrium through flow. When scientists recreate these effects in the lab, they are not merely imitating nature, they are uncovering its hidden language. Each experiment reveals how gravity might emerge from the collective behavior of countless quantum degrees of freedom. Each sound wave traveling through a condensate is a message from the microscopic world, whispering that the geometry of the cosmos could be nothing more than the large-scale echo of quantum motion. If this is true, then the vacuum of space is not empty at all. It is a sea of quantum fluctuations, an invisible fluid whose motion gives rise to gravity and inertia. Particles move through it like ripples through water, their masses emerging from how they interact with the flow. The Higgs field already hints at this idea. It fills space, giving mass to matter through interaction. But perhaps there are deeper fields still, underlying both the Higgs and spacetime itself, unifying them in a single superfluid continuum. The notion that space could behave like a superfluid is not new, but the evidence has never been so suggestive. The equations of general relativity can be rewritten to look like those of fluid motion, and the experiments confirm that this resemblance is not coincidence. It is structure. The laws that govern the bending of light around stars also govern the bending of sound in a moving fluid. The same geometry, the same horizons, the same thermodynamic behavior, only the scale and the medium differ. There is a subtle beauty in this unity. It tells us that the cosmos is self-similar, that the patterns we observe in galaxies, storms, and whirlpools all arise from the same fundamental mathematics. When a vortex forms in superfluid helium, it mirrors the frame dragging that occurs around a rotating black hole. When waves interfere in a condensate, they mirror the interference of gravitational waves across the universe. Every experiment becomes a window into the deep structure of reality, revealing that space-time and matter may be made of the same flowing essence. This perspective changes how we think about existence. The universe ceases to be a collection of objects moving in a void. It becomes a process, a flow of energy and information. The boundaries between substance and space dissolve. Every atom, every photon, every fluctuation becomes part of the same continuum of motion. The geometry of space-time is no longer a fixed background, but a living, breathing fluid in constant flux. But what is this fluid made of? What moves within it? The answer lies not in classical physics, but in quantum theory. Just as a superfluid is composed of countless atoms moving in a single coherent state, space-time might be composed of countless quantum excitations, the smallest possible quanta of geometry. Their collective motion would produce the illusion of continuity we call space and time. If the universe truly behaves like a quantum fluid, then relativity is not fundamental, but emergent. Einstein's equations describe the flow, not the fabric itself. They are the hydrodynamic limit of quantum reality, just as the equations of water dynamics describe the behavior of a sea without ever referencing its molecules. This does not diminish relativity. It reveals its origin. In this view, gravity is not a force, nor a curvature imposed from above, but the manifestation of motion within the deep quantum sea. When mass and energy rearrange themselves, they create ripples in that sea, waves that propagate through the universe as gravity. Those waves carry information, shaping the motion of everything they touch. The cosmos becomes not a structure, but a symphony of flows. This idea will guide us onward. To see space-time not as geometry, but as a dynamic medium, is to glimpse a universe more alive than we ever imagined. In the next step of this journey, we will dive even deeper into the realm where this fluid is born, where quantum mechanics gives rise to the flow of space-time itself, and where the atoms of the universe may truly be atoms of space. When we look at the world through this new lens, the boundary between the tangible and the abstract begins to blur. The universe stops being a set of distant equations and becomes something one can almost feel, not with the hands, but with the mind. Every experiment, every ripple, every vibration in the cold silence of a laboratory becomes a whisper of the cosmos speaking its first language, the language of flow. The evidence continues to grow. When a droplet of superfluid helium rotates, it does not spin like an ordinary liquid. Instead, it forms discrete vortices, tiny whirls that represent the quantized nature of rotation. Each vortex is a perfect, stable structure, its circulation fixed by quantum laws. And yet, when viewed from afar, the droplet moves as if it were a single smooth fluid. Something similar might happen in space-time. The curvature we perceive could emerge from countless microscopic vortices, each one a quantum twist in the flow of the universe. In these superfluids, waves travel without friction. They can circle endlessly without losing energy. This property, dissipationless motion, mirrors the behavior of gravitational waves, which cross the universe for billions of years without fading. No other field behaves with such purity. Every other force decays, interacts, or scatters. But gravity moves untouched. It is as if the medium it travels through, space-time itself, is perfect. This perfection invites a deeper question. In normal fluids, temperature and viscosity govern how the flow evolves. Yet gravity seems to ignore both. It is cold, smooth, and timeless. That might mean that the vacuum of space is already at a kind of absolute zero, a quantum ground state. If space-time is a fluid, it is the most perfect one imaginable, a cosmic superfluid that never slows, never stops, never dissipates. Some theories suggest that beneath the smooth continuum of space-time lies a condensate of quantum fields. Just as atoms in a superfluid share a single quantum state, the entire universe might share one grand wave function. The expansion of space, the formation of galaxies, the very arrow of time could all be patterns within this vast quantum fluid. To us, they appear as separate events, but they are all part of the same flow. Physicists have begun to model this possibility mathematically. Using the equations of hydrodynamics, they find that the same principles governing sound and pressure can describe the curvature of spacetime. Even the Einstein field equations, which form the foundation of general relativity, can be written in the form of conservation laws for energy and momentum, the very equations that describe how fluids flow. This is more than a coincidence. It suggests that relativity itself might be a large-scale approximation of fluid dynamics occurring in an invisible quantum medium. When one studies these models, a remarkable symmetry emerges. The motion of spacetime around a massive object resembles the flow of a fluid around an obstacle. The event horizon of a black hole resembles the critical surface, where a flow transitions from subsonic to supersonic. The expansion of the universe resembles the outward rush of a superfluid after a sudden release of pressure. Everywhere we look, the mathematics repeats itself, echoing the same structure across vastly different scales. In the laboratory, scientists can now simulate cosmic expansion by changing the density of a condensate, creating a miniature version of the universe's early inflation. They can simulate gravitational lensing by shaping the flow of the fluid so that waves curve around dense regions. They can even reproduce the Hawking effect, showing that temperature and entropy emerge from motion. Each experiment confirms that gravity and fluid flow are bound by the same rules, that curvature and flow are two ways of describing the same thing. This realization is not merely technical, it is philosophical. It tells us that the universe is not a frozen architecture, but a process, a ceaseless transformation of energy and information through the medium of space-time. The geometry we see is only the surface of the flow. Beneath it lies a deeper order, invisible but active, connecting every particle and every wave in a vast continuum of motion. And if space-time is a fluid, then our own existence is part of that motion. Every thought, every breath, every flicker of light in our eyes is a small perturbation in that great flow. We are made of the same field that bends around stars and echoes through galaxies. We are not separate from the cosmos, we are patterns in its current. There is a kind of humility in this view. It reminds us that matter is temporary, but motion is eternal. The river of space-time flows through us, carries us, and reshapes us, even as we attempt to understand it. Our physics, our instruments, our theories, they are the small ripples of consciousness within the great ocean that gave birth to them. From the perspective of this flowing universe, the old question, what is gravity, begins to change. Gravity is not a force pulling objects together. It is the natural consequence of how energy and information move through the cosmic fluid. When energy gathers in one region, it changes the local flow, guiding nearby matter along curved paths. What we call attraction is simply the tendency of the fluid to restore equilibrium, to keep the flow smooth and continuous. It is an elegant idea, but also an incomplete one. For if space-time is a fluid, we must ask, what gives rise to that fluid itself? What are its microscopic constituents, its atoms of existence? If we could zoom in far enough, beyond the Planck scale, what would we see? This question leads us into the next chapter of our journey, where the very nature of space and time dissolves into quantum reality. There we will encounter the idea that space-time is not fundamental but emergent, arising from the collective behavior of countless quantum entities, the way a superfluid arises from individual atoms. It is there, in the deep quantum sea, that the flow of gravity begins, not as geometry, but as information, not as curvature, but as coherence. The universe may be the grandest condensate of all, a superfluid of reality itself. And if that is true, then the flow of gravity is not a metaphor, but a literal current, a river that runs beneath the surface of everything we know. If space-time behaves like a fluid, then the next question is inevitable. What is that fluid made of? Every river has its water molecules, every ocean its waves. So too must the flow of gravity have its hidden building blocks. Beneath the smooth continuum of space-time, beneath the curvature described by Einstein, there may exist a deeper quantum structure, invisible to our eyes, yet responsible for everything we call motion, geometry, and time. To glimpse this hidden layer, we must look to the frontier where relativity and quantum mechanics collide. At the Planck scale, where distances are smaller than 10 to the power of minus 35 meters, the smooth surface of space-time begins to dissolve. Quantum uncertainty overwhelms geometry. Distances fluctuate. Time itself loses meaning. It is here that the universe reveals its most secret nature. Some physicists believe that space-time is not fundamental, but emergent, that it arises from something deeper, just as the smooth flow of a superfluid emerges from the quantum coherence of its atoms. This is the essence of the superfluid spacetime hypothesis, explored by researchers like Grigory Volovic, John Moffat, and Stefano Liberati. In this vision, the universe behaves as a vast quantum condensate, formed from fundamental excitations that we have not yet seen. These excitations are not particles in the usual sense. They are the building blocks of geometry itself, the atoms of space and time. In such a model, gravity is no longer a fundamental force. It is a collective effect, an emergent behavior of the quantum liquid we inhabit. When that liquid flows, we perceive the flow as the curvature of spacetime. When it oscillates, we perceive those oscillations as gravitational waves. The field equations of Einstein, which describe the bending of geometry, become the hydrodynamic equations of this deeper fluid. Imagine holding a drop of water in your hand. To you, it feels smooth and continuous. But if you could shrink yourself down to the scale of its molecules, you would see a world of ceaseless motion, atoms colliding, vibrating, forming and breaking bonds. The fluid's apparent smoothness is an illusion created by your limited perspective. The same is true of spacetime. From afar, it looks smooth. Up close, it may be granular, foamy, and alive with quantum motion. In this view, the entire universe is a quantum liquid that condensed from a more chaotic primordial state. At the earliest moments after the Big Bang, when temperatures and densities were unimaginably high, spacetime itself may not yet have existed. Instead, there was only a turbulent sea of quantum fields, fluctuating wildly, with no definite notion of distance or duration. As the universe cooled, this chaos underwent a phase transition, much like water freezing into ice or vapor condensing into liquid. The result was the smooth, continuous spacetime we now inhabit. The mathematics of this process hints that the birth of spacetime could have been an act of condensation, a quantum phase transition of the universe itself. Just as cooling helium transforms into a superfluid at a critical temperature, the early universe might have transformed into the spacetime we know when its energy fell below a certain threshold. Before that, gravity may not even have existed. It would have emerged only when the underlying fluid condensed, giving rise to the curvature and flow that shape reality. In this picture, what we call vacuum is not empty. It is a medium, a perfect, frictionless quantum liquid that permeates everything. The so-called vacuum energy that drives cosmic expansion is simply the energy stored in this medium's ground state. Its fluctuations give rise to particles, fields, and radiation. When matter moves through it, the fluid responds, adjusting its flow. That adjustment is what we experience as gravity. Even the constants of nature, the speed of light, the strength of gravity, the fine structure of atoms, may be properties of this medium, like the viscosity and density of a liquid. In different regions or at different energies, those constants could shift slightly, just as a fluid's behavior changes with temperature and pressure. This idea bridges cosmology with condensed matter physics, suggesting that our universe is less like a void and more like a vast, self-organizing system in equilibrium. One of the most striking consequences of this model is that it naturally explains why spacetime is so stable. A true vacuum, in the quantum sense, would be unstable to small perturbations. Yet the spacetime we inhabit endures. That endurance could come from the coherence of the quantum condensate, its ability to absorb disturbances and restore equilibrium. When a black hole forms, the fluid responds by creating a vortex, isolating the disturbance within a boundary we call the event horizon. When gravitational waves travel, they ripple through the fluid without decay, sustained by its perfect coherence. This coherence is not metaphorical. It is the same principle that allows superfluids to flow forever without friction. In helium cooled below 2 degrees Kelvin, quantum mechanics locks every atom into a single collective state. The entire fluid becomes one macroscopic wave function. It cannot be disturbed without disturbing all of it. That same idea may apply to the universe itself. The spacetime continuum could be a single cosmic wave function. one that unites every particle and every field into a shared state of quantum order. If that is true, then we live inside a quantum superfluid of unimaginable scale. Its ripples are gravity, its waves are light, its turbulence is creation itself. When galaxies spin and merge, they send shock waves through this cosmic liquid. When black holes form, they stir vortices that never die. Every phenomenon we observe, from the bending of light to the rhythm of time, is a manifestation of the motion of this quantum ocean. The implications are profound. It means that reality itself may be emergent. Geometry, time, and matter are not separate things, but patterns within the same flow. The distinction between substance and space dissolves. All that exists is motion, coherent, continuous, eternal motion. To many scientists, this vision offers a unification long sought after. It suggests that general relativity and quantum mechanics are not conflicting descriptions, but complementary layers of the same reality. Relativity describes the large-scale flow of the quantum liquid. Quantum mechanics describes its microscopic vibrations. Between them lies the full story of the cosmos. And yet, even as this vision grows clearer, its details remain elusive. We do not yet know what the atoms of space-time are or how they interact. We cannot see them directly, for their scale is too small and their energies too high. But their presence may be felt in subtle ways, in the tiny fluctuations of the cosmic microwave background, in the noise of gravitational waves, or in the entropy of black holes. Each of these phenomena may be a window into the quantum fluid beneath. So far, we have seen space behave like a fluid, and we have begun to suspect that it is one. But to understand how this quantum liquid gives rise to gravity, we must study its thermodynamics, the way it stores and transfers energy, the way it flows toward equilibrium. Only then can we grasp how motion, information, and geometry are bound together in the same current. If space-time is indeed a quantum liquid, then its properties must obey the laws of thermodynamics. Every fluid, whether water, air, or plasma, has temperature, pressure, and entropy. These are not optional features, they are inevitable consequences of motion. The same must be true for the fabric of the universe itself. Yet when we look at space-time, we do not see temperature or pressure directly. We see only curvature. We see stars bending light, galaxies forming filaments, black holes shaping the paths of time. Still, hidden within that geometry lies a deeper order, the thermodynamics of space-time. At first glance, this may sound abstract, but the link between gravity and thermodynamics is one of the most remarkable discoveries of modern physics. It began with the study of black holes. When Jacob Bekenstein proposed that black holes possess entropy, a measure of disorder or information content, it changed everything. Until then, physicists believed that black holes were simple, featureless objects described only by mass, charge, and spin. But entropy meant complexity, hidden information encoded on the event horizon. Soon after, Stephen Hawking discovered that black holes also have temperature. They emit radiation, faint but real, caused by quantum fluctuations near the horizon. This was more than a theoretical curiosity. It was evidence that space-time, when curved intensely enough, behaves thermodynamically. The surface, gravity of the horizon determines the temperature, while the area of the horizon determines the entropy. These relationships mirror exactly the laws of thermodynamics that govern ordinary fluids. This was not coincidence. It was the first clue that gravity might emerge from deeper statistical behavior, just as temperature emerges from the random motion of atoms. If space-time has entropy and temperature, then it must have microscopic degrees of freedom, hidden variables that carry energy and information. In a normal fluid, those variables are the molecules. In the quantum liquid of space-time, they are the atoms of geometry, invisible yet essential. The realization that space-time behaves thermodynamically led to a radical idea proposed by Ted Jacobson in 1995. He asked a simple but profound question. What if Einstein's field equations, the very equations that describe gravity, are themselves a thermodynamic law? When he explored the mathematics, the answer was yes. By applying the first law of thermodynamics to every small patch of spacetime, relating heat flow to entropy change, he derived the Einstein equations directly. They were not fundamental after all. They were emergent, just like the equations that describe pressure and flow in a fluid. In this vision, spacetime is a system in local equilibrium. Energy flows across horizons just as heat flows through a fluid. When energy crosses a boundary, entropy changes, and spacetime responds by curving. The curvature is not imposed by some external force. It is the system's natural reaction, the way a fluid adjusts to maintain balance. The universe is, in essence, a self-regulating medium. Its geometry evolves to keep its internal thermodynamics consistent. This connection transforms our understanding of what gravity is. Gravity becomes not a force, but a manifestation of entropy and information flow. When matter moves, it disturbs the local distribution of information in spacetime. The system responds by rearranging its geometry, guiding matter along paths that restore equilibrium. Those paths are what we call geodesics. They are the lines of least resistance in the flow of spacetime's information field. If the analogy holds, then the universe itself behaves like a quantum thermodynamic fluid. Every region of space has a temperature associated with acceleration, a fact revealed by the Unruh effect. According to this principle, an observer who accelerates through empty space perceives a bath of thermal radiation, even when an inertial observer sees none. Motion through the vacuum creates heat. The faster you accelerate, the hotter the radiation becomes. This means temperature is not an external property, but an intrinsic aspect of motion in spacetime. Such insights reveal that spacetime has a kind of internal energy, what physicists call gravitational energy density. This energy density determines curvature, much as pressure gradients determine the shape of a fluid's flow. In a very real sense, Einstein's equations can be rewritten as an equation of state, relating energy, entropy, and temperature. The same framework that describes the expansion of gases can describe the expansion of the universe. This correspondence goes deeper still. In the language of statistical physics, macroscopic quantities like pressure and temperature emerge from the collective behavior of microscopic constituents. We never see the individual molecules directly. We see only their average effects. Likewise, we never observe the atoms of spacetime directly, but we feel their collective influence through curvature and gravity. What we call the smooth flow of time is the large-scale behavior of countless quantum transitions occurring beneath our awareness. If this is true, then every gravitational phenomenon, every orbit, every wave, every collapse, is a thermodynamic process. Black holes radiate because they seek equilibrium. The universe expands because its vacuum energy drives a pressure difference. Even inertia, the resistance to acceleration, may be a manifestation of the spacetime fluid's effort to preserve balance. Every motion is part of the cosmic flow toward thermodynamic harmony. In this light, the boundary between quantum mechanics and relativity begins to dissolve. Quantum theory governs the microscopic behavior of the spacetime fluid. Relativity describes its macroscopic flow. The two are not separate, but complementary. The strange non-locality of quantum entanglement and the smooth geometry of spacetime are different faces of the same underlying process. Entanglement links the microscopic quanta of the fluid, ensuring coherence, while curvature describes the large-scale pattern of that coherence. The universe then becomes a self-organizing system of information flow. Each region of spacetime communicates with every other, exchanging energy and entropy through invisible currents. This communication gives rise to the geometry we perceive. Gravity is the shadow of this information exchange, the macroscopic expression of the microscopic dance. Such a picture makes the cosmos feel alive. It is not a cold mechanical structure, but a dynamic equilibrium of flows, constantly adjusting, constantly renewing itself. The laws we know are not fixed decrees, but emergent relationships, maintained through the ceaseless motion of the quantum liquid. To test this vision, physicists look for signs of discreteness in the fabric of spacetime, tiny departures from the continuous geometry predicted by relativity. These could appear as fluctuations in gravitational wave signals, or as noise in the polarization of the cosmic microwave background. Some researchers propose that, just as water waves reveal the structure of their medium, the ripples of spacetime might reveal hints of its atomic nature. If those hints are found, they would confirm what this emerging picture suggests: that the universe is not built upon emptiness, but upon motion itself. Spacetime would stand revealed as a quantum liquid, its geometry an expression of energy flow, its gravity a form of pressure and temperature in perfect balance. But if spacetime flows, then it must also carry information. Every motion, every wave, must transport something through the medium. To understand the true nature of gravity, we must therefore look not only at how energy moves, but at how information flows through the quantum fabric of the universe. That flow, invisible but constant, may be the true essence of gravity, the hidden current that underlies every force and every form. The deeper one contemplates this vision, the more extraordinary it becomes. For if spacetime is a quantum liquid, then every movement of matter and light is an expression of its flow. The fall of an apple, the orbit of a planet, the dance of galaxies, all are ripples within this invisible ocean. The cosmos is not built upon a foundation of static geometry, but upon a living current that moves through every atom and every heartbeat of reality. To perceive this, one must let go of the idea of the universe as a structure and begin to see it as a process. Structures can be built and destroyed, but processes continue. A wave has no edges, no fixed parts, and yet it exists. It carries energy, information, and rhythm. The same is true of spacetime. Its curvature, its expansion, and its flow are not the behavior of something passive, but of something alive. The quantum nature of this fluid begins to reveal itself through theories like loop quantum gravity. In this framework, spacetime is made of discrete quanta, nodes and links in a vast network called a spin network. Each node represents a small chunk of space, each link a surface connecting one region to another. Together, they form a web of geometry, vibrating with quantum information. When this network is coarse-grained, when we step back far enough, it appears as the smooth continuum of relativity. The flow of gravity emerges from the collective motion of these microscopic quanta, just as the flow of water emerges from countless molecules. This concept changes everything. Space and time are not containers for reality, they are products of it. The geometry of the universe is born from relationships. From the way these quantum nodes interact, exchange information, and evolve. When energy passes through the network, the connections rearrange, and the resulting change is what we perceive as curvature. Gravity is not a separate field acting on space-time. It is the manifestation of the network's own dynamics. Other approaches echo this idea. In causal dynamical triangulations, space-time emerges from the self-organization of simple building blocks, each one a small geometric fragment. In the holographic principle, the information content of a region of space can be represented on its boundary, like a fluid whose surface encodes everything that happens within. Across these theories, the same message repeats: geometry is emergent and gravity is collective. When viewed this way, the parallels with condensed matter physics grow stronger. Just as phonons are the collective vibrations of atoms in a solid, gravitational waves may be the collective excitations of spacetime's microscopic structure. They are not fundamental quanta, but emergent phenomena, patterns in the flow of the underlying fluid. Each wave carries information about the state of the medium, its density, coherence, and energy. By studying these waves, we may one day decode the hidden architecture of the quantum liquid itself. This connection also reveals why gravity is so weak compared to other forces. In the quantum liquid picture, gravitational effects arise from the collective motion of an enormous number of microscopic elements. The strength of the interaction felt by any individual particle is therefore diluted across the whole medium. The same reason that sound waves are gentle compared to molecular forces applies here. Collective excitations are smooth and subtle, not violent and direct. Gravity's weakness is a reflection of its universality. It acts everywhere because it belongs to the fabric of everything. In this cosmic superfluid, every region of space communicates with every other through quantum entanglement. This entanglement binds the microscopic quanta of space-time into a coherent whole. When entanglement is lost or redistributed, the geometry changes. Gravity, in this interpretation, is not the result of mass-bending space-time, but of entanglement adjusting itself to maintain equilibrium. The more mass and energy concentrated in one area, the more the local information density changes, and the more the surrounding space-time rearranges its flow. Such an interpretation blurs the line between physics and information theory. It suggests that the laws of motion, energy, and geometry are all expressions of how information is stored and transmitted in the universe. The quantum liquid of space-time is not made of matter, but of information, encoded in wave functions, correlations, and probabilities. Reality is computation performed by the flow of this cosmic fluid. Every interaction, every gravitational wave, every flicker of light is a calculation in the grand algorithm of existence. This perspective unites many seemingly separate discoveries. The entropy of black holes, the Unruh temperature of acceleration, and the thermodynamic derivation of Einstein's equations all emerge naturally from the behavior of this fluid. The horizon of a black hole becomes a surface of maximum information density, a place where the flow of entanglement saturates. The curvature of space-time around mass becomes the macroscopic pattern of that flow. The arrow of time becomes the direction of information's movement toward equilibrium. When we see it this way, the universe becomes comprehensible not as a static object, but as a vast system, evolving through the flow of information. Time itself may be nothing more than the unfolding of that flow. The past, present, and future are not separate entities, but different regions of the same current, moving from lower to higher entropy, from simplicity to complexity. Yet, for all its clarity, this picture also humbles us. We have not yet touched the bottom of this cosmic sea. We can feel its motion through the curvature of space, detect its ripples as gravitational waves, infer its temperature from black holes, and measure its pressure in the expansion of the cosmos. But we have not seen the liquid itself. We live within it, as fish live within the ocean, sensing only the currents, but never the water. Perhaps that is the ultimate irony of consciousness. The very medium that allows us to think and observe is the one we cannot perceive directly. We are made of the flow we seek to understand. Our minds are vortices within the quantum sea, aware of themselves, but blind to the substance that sustains them. Still, we continue to dive deeper. Each discovery brings us closer to the realization that space-time is not merely the stage, but the story itself, a quantum liquid whose motion gives birth to matter, energy, and even thought. The physics of this liquid is the physics of existence. In the chapters ahead, we will explore how this quantum liquid behaves thermodynamically, how heat, entropy, and information flow shape the curvature of space-time, and how Einstein's equations may emerge as the equilibrium condition of a deeper quantum fluid. We will see that the universe is not governed by geometry alone, but by the same principles that govern the flow of air, water, and light, the principles of balance, continuity, and motion. For in the end, The flow of gravity may be nothing more than the universe seeking harmony within itself, a current of information and energy maintaining its eternal equilibrium. Every flow has its balance. Every motion, no matter how vast, follows the quiet rules of energy and equilibrium. If space-time truly behaves as a quantum liquid, then its geometry, its waves, and its currents must obey the same principles that govern every other fluid, the laws of thermodynamics. This realization changes how we understand gravity. It tells us that what we call curvature may be the visible shadow of a deeper thermodynamic process, that every event horizon, every expansion of the universe, every gravitational wave is part of a cosmic exchange of heat, entropy, and information. The connection between gravity and thermodynamics first emerged from the blackest of places, the edge of a black hole. For centuries, black holes were thought to be absolute voids, regions of no return where matter and light vanish forever. They seemed timeless and featureless, perfect absorbers that swallowed everything and gave nothing back. But nature, as always, concealed complexity behind simplicity. When Stephen Hawking and Jacob Bekenstein looked closer, they found that black holes are not inert. They radiate, they have temperature, entropy, and even pressure. In other words, they live by the same laws that govern gases, oceans, and stars. This discovery began with the idea of information. When matter falls into a black hole, what happens to the information it carries? Does it vanish forever? According to the laws of quantum mechanics, information cannot be destroyed. It must go somewhere. Bekenstein realized that the area of a black hole's event horizon, the boundary separating the inside from the outside, increases whenever matter falls in. He proposed that this area is a measure of the black hole's entropy. The larger the horizon, the more information it contains. Then, Hawking took the next step. Using quantum field theory in curved spacetime, he showed that black holes must emit a faint thermal radiation caused by the quantum fluctuations near the horizon. The temperature of this radiation is inversely proportional to the black hole's mass. Large black holes are cold, small ones are hot. The result was astonishing. A region of pure geometry, a curve in spacetime, behaving exactly like a thermodynamic system. This was the first sign that the laws of thermodynamics and the laws of gravity are the same at a deeper level. Each horizon has a temperature, each curve a pressure, each flow a balance of energy and entropy. The Einstein field equations, long believed to describe pure geometry, began to reveal themselves as the equations of state of a hidden fluid. In them, the curvature of space-time plays the role of pressure, and the energy density of matter acts as heat. The universe itself becomes a grand equilibrium system, seeking balance between its parts. Jacobson's insight made this connection explicit. He showed that if one assumes that the laws of thermodynamics apply locally to every small region of spacetime, that heat flow across a tiny patch of horizon is proportional to the change in entropy. Then one can derive Einstein's equations directly. This means that gravity is not fundamental. It is emergent. It arises naturally as the thermodynamic response of spacetime to the flow of energy and information. The elegance of this idea lies in its simplicity. Every time energy crosses a horizon, spacetime adjusts its geometry to maintain the first law of thermodynamics, the balance between heat, work, and internal energy. In this view, gravity is not a force, but an accounting system, keeping track of the universe's energy transactions. When matter moves, spacetime bends to ensure conservation of energy and entropy. Even the mysterious expansion of the universe can be described this way. The vacuum energy that drives cosmic acceleration acts like a pressure difference within the fluid of spacetime. It pushes outward, stretching the geometry as heat pushes against the walls of a container. The cosmological constant, that small but persistent term in Einstein's equations, is not a mathematical oddity, but a thermodynamic pressure, the signature of the vacuum's energy density. The more we explore this analogy, the more literal it becomes. The Unruh effect tells us that acceleration itself creates temperature. An observer at rest in space feels nothing, but an accelerating observer perceives a warm glow of particles, a bath of radiation surrounding them. This temperature is proportional to the acceleration. Motion through spacetime is enough to create heat. This means that temperature is not an external property. It is built into the very fabric of motion and gravity. The implications are profound. If temperature and entropy are woven into the structure of spacetime, then thermodynamics is not a separate branch of physics. It is the foundation of all physics. Every field, every interaction, every wave is part of a vast thermodynamic system, a universe that maintains equilibrium through continuous flow. In this thermodynamic universe, black holes are no longer mysteries, but natural consequences of equilibrium. Their horizons mark the boundaries between regions of differing information density. They are not singularities of destruction, but surfaces of transformation, where the flow of energy and information balances perfectly. When matter crosses the horizon, its information is not lost, but encoded on the surface, stored as microscopic degrees of freedom, the same way molecules at the surface of a fluid store the energy of its motion. This realization gives rise to the holographic principle, which states that the information contained in a region of space can be represented on its boundary. The universe, then, may be holographic by nature. Its volume, filled with fields and waves, is simply the projection of information stored on the surfaces that enclose it. Gravity, in this context, becomes the fluid flow of information across those surfaces. Such a universe is both elegant and strange. Its geometry is not fixed but dynamic, shaped by entropy gradients and energy flow. The curvature of spacetime is a reflection of the underlying information flow. Matter follows curved paths not because it is pulled by invisible forces, but because the flow of entropy guides it toward balance. This unites the old and the new. The classical picture of Einstein and the quantum vision of thermodynamics merge into one continuous story. The smooth geometry of relativity emerges from the statistical behavior of quantum bits of information. Heat, entropy, and curvature become different expressions of the same principle, that flow and equilibrium govern everything. In this picture, the universe is not a mechanical system of particles obeying rigid laws. It is a self-regulating organism of flows, always adjusting to preserve its balance. Entropy does not signify decay, but transformation. Every star that burns, every planet that cools, every black hole that radiates participates in this cosmic thermodynamic process. If gravity is the language of flow, then thermodynamics is its grammar. It tells the universe how to move, how to exchange, how to breathe. The expansion of space, the motion of galaxies, the fall of an object, all are governed by the same rule. The universe flows toward balance. And yet, behind this elegance lies mystery. For if space-time behaves thermodynamically, then its temperature, entropy, and pressure must come from something. The microscopic degrees of freedom, the atoms of space-time, must exist. They are the source of this behavior, the unseen particles of the cosmic fluid. To find them is to find the foundation of reality itself. In the next part, we will look deeper into this mystery, how the thermodynamics of space-time reveals the flow of information, and how gravity itself may be nothing more than the universe's way of processing and redistributing that information. Everywhere we look, from the smallest atom to the largest galaxy, we see balance and imbalance intertwined. Heat flows from hot to cold. Energy spreads until equilibrium is restored. Entropy, the quiet arrow of time, always increases. The universe seems to prefer smoothness, to erase gradients, to even out the differences. Yet it is precisely these differences, in temperature, in density, in energy, that give rise to motion. Without imbalance, there would be no flow. Without flow, there would be no time. If space-time is a thermodynamic system, then it must also obey this principle. The universe flows because it is always seeking balance. The curvature of space, the movement of matter, the expansion of the cosmos, these are not arbitrary motions, but the response of a vast system striving to equalize its internal energies. Gravity, in this sense, becomes the tendency of space-time to redistribute information and restore equilibrium. To understand this, we must see information as physical. Every particle, every field, every fluctuation carries information, not just about what it is, but about where and when it exists. When matter moves, it changes the local density of information. That change ripples outward through the space-time fluid, adjusting geometry to reflect the new distribution. What we perceive as gravitational attraction is the space-time medium adjusting its flow to conserve information. This is the heart of the idea known as entropic gravity, developed by Eric Verlinde and others. It proposes that gravity is not a fundamental force, but an emergent phenomenon, arising from changes in the information content of space-time. When matter moves, the entropy of the surrounding region changes, creating an entropic gradient. The system responds by moving toward higher entropy, by reshaping geometry in a way that we interpret as gravitational pull. In this picture, every gravitational interaction is a flow of information. Entropy increases as matter rearranges. The motion of planets, the fall of an apple, the merging of galaxies, all are driven by the universe's constant search for thermodynamic equilibrium. Space and time are not merely arenas in which this occurs. They are active participants, reshaping themselves to maintain the balance. The beauty of this approach lies in its unity. It connects three great pillars of physics: relativity, quantum mechanics, and thermodynamics, into one continuous framework. Einstein's equations describe how energy determines curvature. Quantum mechanics describes how information behaves. Thermodynamics describes how systems flow toward equilibrium. In entropic gravity, these are all aspects of a single process: the flow of information through the quantum fabric of space-time. Every horizon in the universe, from a black hole's boundary to the cosmological horizon that defines the edge of the observable universe, acts like a thermodynamic surface. Each has temperature and entropy. Each radiates information. When energy crosses such a surface, information flows with it, and the geometry adjusts to preserve balance. The surface area of a horizon measures how much information it can store. 1 bit for every small patch, roughly the size of the Planck area. The total capacity of the universe to store information is therefore proportional to the total area of its boundaries, not its volume. This is the essence of the holographic principle. In this holographic universe, space-time itself becomes the hydrodynamics of information. Its curvature, its waves, its flow, all are the macroscopic manifestations of microscopic entanglement patterns. Just as the motion of water molecules creates waves and currents, the rearrangement of quantum entanglement creates geometry and gravity. When entanglement density changes, space-time bends. When coherence is lost, energy radiates away. The geometry we see is simply the map of how information moves. This realization changes the meaning of motion. When an object falls, it is not being pulled by a mysterious force. It is following the gradient of information density in the space-time fluid. The closer it moves toward a region of higher entropy, the smoother the overall flow becomes. The universe uses motion to restore balance. What we experience as acceleration is, at its core, a thermodynamic adjustment in the geometry of information. The same reasoning applies to cosmic expansion. The universe expands not because something external pushes it, but because the information density of the vacuum drives the geometry outward. The vacuum itself has entropy, a measure of the quantum fluctuations that fill empty space. As the universe evolves, that entropy increases. Space stretches to accommodate it, just as a gas expands to fill its container. The acceleration of cosmic expansion, attributed to dark energy, may be nothing more than the natural thermodynamic behavior of the space-time fluid adjusting to its own quantum information content. This understanding also sheds light on one of the oldest puzzles in physics, the arrow of time. Time moves forward because entropy increases. But in the thermodynamic universe, entropy is not an external measure of disorder. It is the flow of information through the medium of spacetime. Time is the direction in which information spreads. The past is where information was concentrated. The future is where it becomes diffuse. The flow of time is the flow of entropy, and both are expressions of the same underlying current. It is humbling to realize that even our own consciousness may be part of this thermodynamic process. Every thought, every memory, every act of perception increases entropy slightly, changing the local flow of information. Our awareness is not separate from the universe, but part of its ongoing attempt to balance itself. We are vortices in the current, temporary but real, formed by the same quantum fluid that shapes galaxies and black holes. If the laws of thermodynamics govern space-time, then the temperature of the vacuum, the entropy of horizons, and the flow of energy across them are not coincidences, but necessities. They are the inevitable behavior of a system that seeks equilibrium across all scales. The Einstein field equations, in this view, are simply the macroscopic expression of that equilibrium, the universe's bookkeeping of heat, energy, and information. This view may one day explain why gravity is universal. Every form of energy, every particle, interacts with spacetime not through charge or spin, but through entropy. All energy carries information, and all information flows through the same medium. That is why gravity acts on everything equally, because everything participates in the thermodynamics of spacetime. In this grand picture, the universe is a self-correcting, self-sustaining fluid of information. It flows toward equilibrium, but never reaches it, for the process itself gives rise to time, structure, and life. Every star burning, every black hole radiating, every galaxy drifting through the dark, all are eddies in the great thermodynamic current. But what happens when this current becomes turbulent? When space-time itself swirls, twists, and collides with itself, as in the merging of black holes or the birth of the universe? If the cosmos is a fluid, then turbulence must exist within it. The next step of our journey will lead us there, to the places where gravity becomes chaotic, where the flow of space-time curls into vortices, and where the calm equilibrium gives way to the storm. In the vast stillness between galaxies, one might imagine nothing happens. Yet even in that silence, energy flows, entropy rises. Invisible currents of information move through the fabric of space-time like tides beneath a frozen sea. The universe is never still. Every fluctuation of the quantum vacuum, every photon drifting through cosmic darkness, is part of a ceaseless thermodynamic dialogue, a whisper between matter, energy, and geometry. The profound realization that gravity may be thermodynamic in nature reshapes our understanding of reality itself. It implies that the universe does not obey the laws of thermodynamics. It is those laws, written in the language of curvature and motion. Space and time are not separate entities on which physics occurs. They are the manifestation of energy-seeking balance. The Einstein equations describe not a static geometry, but the equilibrium condition of a dynamic, self-regulating fluid. When energy flows, space-time responds. When information changes, entropy shifts. These shifts are not hidden behind the veil of mathematics. They are the heartbeat of the cosmos. Every horizon, whether the boundary of a black hole or the cosmic horizon of the observable universe, is a thermodynamic surface where this flow is most intense. Across these boundaries, energy, heat, and information exchange places, always maintaining the cosmic balance. Black holes, once thought to be devourers of all things, now stand revealed as engines of information flow. The Hawking radiation they emit is not waste, it is equilibrium asserting itself. Each quantum of radiation carries away a fragment of the information encoded on the horizon, ensuring that the total balance of entropy is preserved. Even as the black hole evaporates, the information it once held does not vanish. It transforms, diffusing into the surrounding spacetime. The universe never loses information. It merely changes its form. This idea suggests a deep symmetry in the cosmos. Every process of collapse has its counterpart in expansion. Every loss of order in one place creates structure in another. Entropy does not destroy, it transforms. In this way, thermodynamics becomes the unifying language of creation and dissolution, of stars forming and dying, of galaxies spinning and merging, of the universe expanding and cooling. Every act of transformation is part of the same universal cycle of flow. Some physicists suspect that this balance extends even to the vacuum itself. The apparent emptiness of space is not empty at all. It seethes with quantum fluctuations, virtual particles appearing and disappearing in pairs, carrying energy and entropy that average to zero over time. Yet their existence ensures that spacetime never reaches absolute equilibrium. There is always a slight imbalance, a residual pressure, what we call vacuum energy. This faint but persistent pressure drives the expansion of the universe. It is the thermodynamic pulse of the cosmos, the signature of its constant self-adjustment. This interpretation makes the cosmological constant not a problem to be solved, but a property to be understood. It represents the ground state energy of the spacetime fluid, the lowest level of vibration in the quantum sea. The smallness of its value, a tiny number compared to the energy scales of particles and fields, reflects the near-perfect balance of the cosmic fluid. The universe is almost, but not quite, in equilibrium. That small imperfection is what allows it to evolve, to expand, to create structure and life. The idea that the cosmos lives at the edge of equilibrium also explains why time flows. A perfectly balanced system would be timeless. Nothing would change. But because the universe is never perfectly balanced, because energy and entropy are always shifting slightly, time moves forward. The arrow of time is simply the universe flowing toward a state it will never fully reach. Each moment is the rearrangement of information, each second a step in the journey toward equilibrium. In this sense, thermodynamics does not merely describe the universe, it defines it. Everything we call fundamental, from the forces that shape matter to the quantum fields that define space, may be emergent phenomena of this deeper thermodynamic order. The universe is not governed by laws imposed from above. It is guided by the tendency of systems to evolve toward balance, and by the ceaseless motion that arises when that balance can never be complete. This perspective brings a quiet unity to everything. The same equations that describe the expansion of a gas also describe the expansion of the universe. The same principles that determine the temperature of a black hole determine the energy of space-time itself. Gravity becomes the gentle pressure of the cosmic fluid seeking uniformity. Light becomes the vibration of its energy field. Matter becomes the localized condensation of its flow. All that exists, from quark to quasar, arises from the same thermodynamic river that flows through the fabric of existence. If one could step outside the universe and look down upon it as a whole, perhaps it would appear not as a collection of stars and galaxies, but as a single luminous current, a river of entropy and energy swirling in self-sustaining motion. The galaxies would be eddies, the black holes whirlpools, the radiation the shimmering spray that carries information downstream. It would not be a machine, but a living process. Every motion would be the expression of a deeper drive toward equilibrium. Every event, a note in the great thermodynamic symphony of reality. And we, as conscious observers, are not apart from this flow. The act of observation is itself thermodynamic. Every thought, every sensation, every flicker of awareness consumes energy, increases entropy, and participates in the universal current. We are both products and participants of the same law. The cosmos looks at itself through us, measuring its own temperature, feeling its own pressure, sensing its own flow. As the equations of relativity and quantum theory merge under the banner of thermodynamics, a new vision emerges, not of a cold, mechanical universe, but of one that breathes. A universe whose geometry evolves because its information evolves. A universe whose gravity flows because its entropy flows. The stars do not burn merely to shine, they burn to balance. The galaxies do not rotate by accident. They move to maintain harmony in the great thermodynamic web. But harmony by its nature is never static. Every balance leads to imbalance, every stillness to motion. Somewhere deep beneath this equilibrium, the current of information flows endlessly. Invisible, silent, but real. It is this current that defines gravity, that shapes space-time, that carries the memory of the cosmos from one moment to the next. And so, we reach the heart of the mystery. If gravity is the thermodynamic expression of information flow, what is information itself? What moves through this quantum fluid? And how does it shape the universe we see? The next step of our journey leads us there, into the deep current of reality, where energy, entropy, and knowledge are one and the same, and where the flow of information becomes the very heartbeat of the cosmos. In the great quiet of the cosmos, there is no stillness. Beneath the vast fields of stars, beneath the motion of galaxies, something more subtle flows. Not matter, not light, but information itself. It is the unseen current that threads through every field, every atom, every fluctuation of space-time. Energy and mass may be its vessels, but information is its cargo. It is this current, invisible yet omnipresent, that gives rise to the force we call gravity. From the perspective of quantum theory, everything that exists carries information. The spin of a particle, the vibration of a string, the position of a planet, all of it encodes data about the state of the universe. Even the empty vacuum, with its flickering virtual particles, holds information in its fluctuations. Nothing escapes this rule. The universe does not allow information to vanish. It only changes form. When mass moves through space-time, it does not merely travel. It alters the density of information in its surroundings. Space-time, as a fluid medium, reacts to this shift. It curves, reshapes, and flows to conserve the total information content. This adjustment is what we perceive as gravity. The apple falls not because it is pulled, but because the information density around Earth's mass is higher, and the universe seeks to equalize it. Gravity is the fluid's way of restoring balance. This concept finds its echo in the idea of entropic gravity, where the pull we feel toward massive objects arises from the gradient of entropy, a gradient of information density in space-time. Eric Verlinder's insight reframed gravity not as a force acting at a distance, but as the natural thermodynamic tendency of the universe to maximize entropy. When matter changes position, it changes the distribution of information. The geometry responds to restore equilibrium, and that response appears to us as gravitational attraction. In this picture, space-time becomes a dynamic information field, its curvature representing the flow of data between regions. Where information is dense, the field compresses. Where information is sparse, it expands. Just as heat flows from hot to cold, information flows from dense to diffuse, guided by the same mathematical laws that govern fluid dynamics and thermodynamics. The Einstein equations become the hydrodynamic equations of this invisible current. Quantum entanglement adds another layer to this vision. When two particles are entangled, their states are connected across space. A change in one instantaneously affects the other, no matter the distance. This strange connection is not a transmission of energy, but a correlation of information within the space-time fabric itself. Entanglement weaves the universe together. It defines the structure of space by determining which parts of the quantum field are correlated. Without entanglement, space would not exist as a continuous entity. It would fragment into isolated regions with no shared geometry. Physicists have discovered that the very shape of space-time may be determined by these entanglement patterns. In the framework known as holographic duality, sometimes called ADS-CFT correspondence, the geometry of a higher dimensional space-time can be constructed entirely from the entanglement structure of a lower dimensional quantum field. This means that space itself emerges from information. The bending of space-time, the flow of gravity, and even the expansion of the universe all arise from the rearrangement of quantum correlations. If this is true, then the flow of gravity is literally the flow of information through the entanglement network of the universe. When energy moves, it changes the entanglement structure. When entropy increases, geometry shifts. The waves of space-time that we detect as gravitational radiation are ripples in this network, oscillations in the pattern of information connecting the cosmos. Consider two black holes spiraling together. As they merge, their horizons twist and stretch, radiating gravitational waves that travel across billions of light years. Those waves carry not only energy, but information about the system, its mass, spin, and structure. When we detect them, we are not merely hearing the sound of space-time. We are reading the data of a cosmic event encoded in the universe's fabric. Information has flowed from one region of space-time to another, carried on the waves of its own geometry. This flow is not limited to extreme events. It occurs everywhere, at every scale. When a planet orbits a star, information flows between them through the curvature of space-time. When light bends around a galaxy, information flows from the geometry to the photon, guiding its path. Even in the emptiest void, where there is no matter and no radiation, the quantum vacuum hums with fluctuations, each one an exchange of information between the virtual particles that briefly exist and vanish. The universe is a vast, continuous conversation conducted in the language of information. In this light, energy and information become inseparable. The first law of thermodynamics, which relates energy conservation to heat flow, becomes identical to the conservation of information. Whenever energy moves, information moves with it. When a star burns, when a black hole evaporates, when a particle decays, the universe's total information content remains constant, though its arrangement changes. The second law, the increase of entropy, is simply the universe's natural tendency to distribute information more evenly over time. This means that time itself may be an emergent property of information flow. The direction of time is the direction of entropy increase, and entropy increase is the spreading of information. Time is not an external parameter ticking independently of events. It is the unfolding of the universe's own computation, the continuous reorganization of data in the space-time fluid. Each moment is a new arrangement of correlations, a new state of the cosmic information network. If this view is correct, then gravity is not merely a curvature of geometry, but the visible form of the universe computing itself. The field equations of general relativity become algorithms describing how information moves through the quantum medium. The speed of light becomes the maximum rate at which information can propagate. The constants of nature become the scaling factors of this grand computation. Reality itself becomes an information processor. Its output, the experience we call existence. Such a view is not metaphorical. It finds grounding in quantum field theory, where information determines the state of every system. Entropy and entanglement are not philosophical ideas, but measurable quantities. We can calculate how much information is stored in a black hole's horizon, how much is carried by gravitational waves, and how it flows when systems interact. The mathematics of these flows matches the mathematics of fluids and thermodynamic systems. The parallel is not poetic, it is structural. If gravity is indeed the hydrodynamics of information, then the universe's geometry is a record of its history, a memory of how information has flowed through time. Each curve, each wave, each horizon encodes data about the past, frozen into the space-time continuum. When we look at distant galaxies, we are reading ancient records of this information flow, imprinted in light that has traveled for billions of years. The universe, in essence, remembers itself. But what happens when this flow becomes disrupted, when information is trapped, twisted, or scattered? How does the universe restore balance when its own current becomes turbulent? To answer that, we must look into the places where gravity reaches its limits. In the swirling chaos near black holes, in the foaming depths of quantum spacetime, where information and geometry blur into one. There, the flow of information no longer runs smoothly. It churns, folds, and reconnects, creating patterns that may hold the key to understanding both the unity and the complexity of the cosmos. For in that turbulence, we may finally see the true face of gravity, not as a static curve, but as a living current of information, endlessly reshaping itself to keep the universe whole. To imagine the universe as a living current of information is to see existence itself in motion. Every particle, every beam of light, every tremor of gravity becomes a messenger of data, passing from one region of spacetime to another. It is as if reality were woven from the transmission of meaning, the silent conversation of the cosmos with itself. The laws of physics are the syntax of this conversation. Geometry is its grammar. Gravity is its rhythm. Quantum entanglement lies at the heart of this rhythm. It is the mechanism by which space-time connects itself. When two particles are entangled, their states become intertwined no matter how far apart they travel. They cease to be separate entities and become a single distributed system. This connection is not a line drawn through space, but a link in the deeper network of correlations that defines what space is. Physicists like Mark van Ramsdonk and others have shown that the geometry of space-time can be derived from patterns of entanglement. The more two regions of a quantum system are entangled, the closer they are in the emergent geometry. The less they are entangled, the farther apart they appear. Distance itself, therefore, may not be a fundamental quantity. It is a measure of correlation strength, an emergent property of information flow. The structure of space is the structure of quantum relationships. When entanglement is lost, space-time tears. When it increases, space-time stitches itself together. Black holes are regions where information becomes trapped, where entanglement connections reach their limit. Their horizons mark the boundaries of communication between regions of the quantum network. The famous paradoxes surrounding black holes, information loss, evaporation, and unitarity, all arise from our incomplete understanding of how information moves across those boundaries. But recent discoveries suggest that information is never truly lost. It may be scrambled, diffused, and transformed, yet always conserved. The surface of a black hole, its horizon, acts as a perfect information ledger. Every quantum that falls in changes the horizon's microscopic state. The total information remains encoded there, hidden but not destroyed. Over time, as Hawking radiation leaks away, the information gradually re-emerges, carried by the correlations between the emitted particles. The universe thus preserves its own memory, even in the face of apparent annihilation. This principle of conservation echoes throughout all scales of physics. Information is the most fundamental quantity of all. It cannot be created or destroyed, only transformed. Every exchange of energy, every interaction between fields, is an exchange of information. This conservation is what gives rise to the symmetries of nature. It ensures that energy and momentum are preserved, that time and space are coherent, that causality endures. Information is the thread that binds the tapestry of the cosmos together. In this sense, gravity can be viewed as the circulation of that thread, the continuous rebalancing of information density across space-time. When matter concentrates in one region, information becomes more tightly packed there. The rest of the universe responds by adjusting its geometry, redistributing correlations to maintain global coherence. That adjustment manifests as gravitational curvature. The flow of information is the flow of gravity. This relationship can be visualized in the language of networks. Imagine spacetime as an immense web of nodes connected by entanglement links. The strength of each link determines the local curvature. When one region gains energy, its connections tighten, pulling the geometry inward. When energy flows outward, the links loosen and space expands. The Einstein field equations become the macroscopic rules that govern this web's equilibrium, the hydrodynamics of its quantum information flow. The holographic principle reinforces this vision. In holographic theories, the information describing a volume of space resides entirely on its boundary, encoded like a two-dimensional pattern that projects a three-dimensional image. This principle is not a metaphor. It is a precise mathematical correspondence. It means that the flow of information across boundaries determines the dynamics within. The curvature of the bulk space is the manifestation of the entanglement structure on its surface. In this view, the universe operates much like a self-sustaining information engine. Boundaries and horizons act as processors, converting local data into geometric change. The vacuum is not empty. It is a dense, self-organizing web of quantum bits constantly exchanging information. Even the quiet regions of deep space are alive with subtle interactions, maintaining coherence through entanglement. The cosmic expansion, the motion of galaxies, the persistence of time, all emerge from this ceaseless communication. The remarkable insight here is that entanglement does not merely connect parts of the universe. It creates the universe. Without entanglement, space would have no connectivity. It would dissolve into isolated points. The continuity of space, the very possibility of motion, depends on the flow of quantum correlations. Gravity, then, is the expression of those correlations seeking equilibrium. When the entanglement network is disturbed, geometry bends to restore balance. This connection between information and geometry is more than conceptual. It has been demonstrated mathematically in holographic models, where the amount of entanglement between regions determines the curvature of the emergent spacetime. The Ryu-Takayanagi formula, for example, relates the entropy of entanglement to the area of minimal surfaces in the bulk geometry, the same relationship that governs black hole horizons. It is a bridge between quantum information theory and the equations of general relativity. Such results suggest that Einstein's field equations are not fundamental but statistical. They describe how the geometry of spacetime changes as the underlying quantum information reorganizes itself. Just as the motion of air molecules gives rise to the macroscopic laws of fluid flow, the rearrangement of entangled quantum states gives rise to the macroscopic laws of gravity. The smooth curves of spacetime are the collective behavior of countless microscopic information exchanges. When we think of it this way, the universe becomes a vast network of computation. Each interaction is a data exchange. Each particle is a qubit. Each horizon is a memory boundary. The expansion of space is not random. It is the unfolding of computation, the growth of the universe's information capacity. The past is recorded in the geometry of spacetime. The present is the processing of that data, and the future is the result waiting to be computed. The great paradox, of course, is that we ourselves are part of this computation. Our thoughts, our memories, our acts of observation are not external to the universe's flow of information. They are small ripples within it. Consciousness may be the reflection of the universe becoming aware of its own information processing, a localized feedback loop within the larger system. We are not separate from the current of gravity, we are made of it. In this view, existence is a process of continuous exchange. Energy flows, entropy rises, information spreads, and geometry evolves. The river of reality has no source and no mouth. it flows within itself, endlessly reconfiguring its patterns. Gravity is its current, guiding the motion of stars, atoms, and thoughts alike. But no flow is perfectly smooth. Even the most serene river hides turbulence beneath its surface. If space-time is truly a fluid of information, then its currents must sometimes twist, eddy, and break, forming structures of complexity that echo through the cosmos. These are the vortices of reality, the whirlpools of gravity where the flow becomes chaotic. To understand them is to glimpse the deep quantum turbulence of space-time itself. And so, as we follow the flow of information deeper into the heart of gravity, the next step awaits: the study of turbulence, of vortices, and of the living storms within the quantum ocean that is space-time. As the understanding of information deepens, a new picture of the universe begins to take shape, not as a collection of particles floating in an empty void, but as a living ocean of quantum data, continuously moving, rearranging, and evolving. This ocean does not sit in space. It is space. Its flow is not bound by geometry. Its flow creates geometry. Each change in the pattern of information alters the curvature of space-time, reshaping reality from the inside out. We, who live within this current, perceive its movement as gravity. When we see the planets orbiting the sun, we imagine a force holding them in place, an invisible hand drawing them inward. But what we are truly seeing is information redistributing itself. The mass of the sun warps the information density of space-time, creating a smooth gradient through which Earth moves. The planet's motion is not compelled, but guided. It follows the most natural path through the flow of information, the path that preserves equilibrium. Einstein's insight that geometry replaces force becomes richer in this context. Geometry is not static, it is alive. Its curves are not drawn once, but constantly rewritten as energy and entropy flow. The field equations become the expression of a self-updating universe, one that recalculates itself at every moment to maintain the conservation of information. This continuous recomputation gives the cosmos its coherence and its beauty. In this framework, energy and information are two sides of one coin. When energy flows, information flows. When information redistributes, geometry evolves. Entropy measures how information spreads. Temperature measures the rate of that spreading. Gravity, in turn, measures how geometry adjusts to accommodate it. The familiar constants of physics, the speed of light, Planck's constant, Newton's constant, are the scaling rules of this vast thermodynamic computation, setting the rhythm of the cosmic flow. Everywhere we look, nature reveals hints of this unity. When a black hole radiates, information escapes in the form of subtle correlations between emitted particles. When two black holes merge, their information contents blend, and the resulting gravitational waves broadcast the record of that event across the universe. Even the gentle undulations of space-time that we detect with our instruments are waves of information, patterns of data moving through the quantum medium of existence. This is not abstraction. It is the literal reality of the cosmos. Information is not an optional description of physics. It is physics. The position of a star, the energy of a photon, the spin of an electron, these are all expressions of stored information. When these change, information flows. When it flows, gravity moves with it. The universe is a single vast computation where every particle is both a symbol and a processor. The concept of entropy ties this together. Entropy is not disorder. It is the measure of possible arrangements of information consistent with what we know. The higher the entropy, the more ways the universe can be. Gravity guides matter in such a way that entropy increases. It ensures that the cosmos evolves toward richer and more complex states. Not chaos, but possibility. This is why structure forms out of apparent simplicity. Galaxies, stars, and life itself are products of gravity's thermodynamic design, the universe's method of balancing energy and information across scales. In this light, creation and equilibrium are not opposites. They are complementary. The universe creates structure precisely to distribute its information more efficiently. every star that forms, every planet that coalesces, every life that thinks is part of the same process, the self-organization of a cosmic information field seeking harmony. What appears as evolution is the unfolding of a computation written in the logic of thermodynamics. The evidence of this process can be found even in the quantum foam, the restless microstructure of spacetime. At the smallest scales, fluctuations in energy create tiny distortions in geometry, momentary surges and eddies in the information field. These quantum fluctuations are the source of everything we observe at large scales. The structure of galaxies, the pattern of cosmic background radiation, even the asymmetry that allowed matter to dominate over antimatter. All of it may trace back to the turbulence of this primordial flow. If the universe is indeed an ocean of information, then gravity is its current. It circulates data through the cosmic medium, maintaining coherence across incomprehensible distances. It carries the memory of every event forward in time. Each gravitational wave that crosses the void is a page in the universe's diary, preserving what happened long after the matter involved has vanished. The cosmos remembers not through text or symbols, but through geometry, through the way space-time itself bends and swells in response to motion, and in that memory lies purpose. The universe is not static, but reflective. Every ripple it creates contains echoes of all the others, connecting the present with the deep past and the far future. To exist within this flow is to participate in the self-awareness of the cosmos, the grand feedback loop of information that we call reality. This vision of gravity as an informational flow leads naturally to another realization. A perfect information fluid would have no resistance, no loss, no decay. Its currents would persist forever, carrying data flawlessly through the ages. In other words, if spacetime is a fluid of information, it must be a superfluid, a medium that flows without friction, that transmits waves without dissipation, that endures unchanged across cosmic time. Evidence for this perfection is already before us. Gravitational waves travel for billions of years without weakening. The geometry of spacetime bends and relaxes without generating heat. The universe conserves its energy and information with infinite precision. These are not the properties of an ordinary medium, they are the signatures of a superfluid, one whose viscosity is zero and whose coherence is total. To think of gravity as a superfluid is to see the universe in motion at its purest form. The stars do not drift through emptiness, but glide through a quantum ocean that never loses energy, never forgets, and never stops flowing. Every black hole, every burst of light, every whisper of radiation becomes a vibration in that cosmic superfluid. And perhaps, just as vortices form in liquid helium or in a Bose-Einstein condensate, the universe itself contains vortices, regions where space-time twists endlessly around itself, holding memory and motion in perfect balance. We have arrived at the threshold of a new understanding. The flow of information is the lifeblood of the universe, and gravity is its circulation. But now we must ask, what kind of fluid is capable of sustaining this perfect eternal flow? The answer lies in the strange and beautiful world of quantum superfluids, where motion becomes timeless and flow becomes absolute. Across the vast reaches of space, the universe behaves with an eerie smoothness. Gravitational waves sweep across billions of light years without losing a whisper of strength. The paths of planets, the motion of stars, the orbits of galaxies all unfold without friction. Nothing slows, nothing drags. It is as though the cosmos were filled not with emptiness, but with an invisible medium of perfect clarity, one through which motion continues forever. This is the first hint that spacetime may not simply resemble a fluid, but may be one, a perfect quantum superfluid whose flow defines reality itself. A superfluid is unlike any other state of matter. In the laboratory, when helium is cooled to near absolute zero, it begins to behave in impossible ways. It flows without viscosity, climbing the walls of its container, circulating endlessly through narrow channels without losing energy. In such a state, motion is eternal. The fluid becomes coherent, as though every atom shares the same wave function. It behaves not as many particles, but as one unified entity, a single quantum organism. This coherence, this unity, is what gives it its miraculous properties. Now imagine space-time at the Planck scale, the unimaginably small realm where quantum effects dominate. There, geometry itself may take on the properties of a superfluid. Instead of being a rigid framework, it may be a condensate of countless microscopic quanta, each one interacting in perfect harmony. The waves that travel through this medium, gravitational waves, would then be like sound waves in a superfluid, moving without resistance, carrying energy and information across the cosmos with perfect fidelity. This vision has been explored by physicists such as Grigory Volovic, Paolo Liberati, and John Moffat, who have proposed that the vacuum of space behaves as a quantum condensate. In their view, general relativity is not fundamental but emergent, the macroscopic hydrodynamics of a deeper quantum fluid. Just as the smooth flow of water hides the chaotic motion of its molecules, the smooth geometry of space-time hides the restless motion of quantum degrees of freedom beneath. Einstein's equations, in this sense, are like the Navier-Stokes equations of space-time. They describe the flow of a fluid too fine-grained to see. This perspective explains one of the universe's most striking features, the near-perfect conservation of gravitational energy. Unlike electromagnetic or nuclear forces, gravity suffers no dissipation. A gravitational wave can pass through an entire galaxy and emerge unchanged. In a normal medium, waves scatter, lose coherence, and decay into heat. But the space-time fluid seems immune to such losses. It is a medium of absolute transparency, a perfect conductor of geometry. If space-time is indeed a superfluid, then black holes become its vortices. In a rotating superfluid, motion cannot occur in arbitrary patterns. It organizes itself into quantized vortices, stable and persistent structures around which the fluid circulates forever. Each vortex represents a singularity of flow, a point where the fluid's phase twists around itself. In the same way, a black hole may be a region where the quantum fluid of space-time loops into a closed rotation. The event horizon would mark the boundary of the vortex, the surface where circulation becomes trapped. This analogy extends even further. In laboratory superfluids, vortices carry quantized angular momentum and can merge or annihilate under certain conditions. When two vortices collide, they release waves that ripple across the fluid. Similarly, when two black holes merge, they radiate gravitational waves that spread through space-time, the echoes of vortical reconnection in the cosmic superfluid. The resemblance is not superficial, it is mathematical. The equations that describe the behavior of these quantum vortices mirror those of the Kerr metric in general relativity, which defines rotating black holes. The superfluid model also offers insight into the apparent rigidity of the vacuum. In a superfluid, long wavelength excitations behave as phonons, collective oscillations that move through the medium at well-defined speeds. These excitations are what we perceive as gravitational waves. The stiffness of the vacuum, its resistance to compression, is what sets the speed of these waves, the speed of light. In this way, the fundamental constant that defines relativity may arise from the elastic properties of the space-time condensate. But if space-time is a fluid, what are its atoms? The answer may lie in quantum gravity. In loop quantum gravity, the geometry of space is quantized into discrete units, tiny loops or nodes that form a network called a spin foam. Each node represents a quantum of volume, each link a quantum of area. Together they form the microscopic structure of space-time. When seen from far away, these quanta blur into a continuous fabric, just as individual molecules blur into a continuous liquid. The superfluid properties of space-time, emerge from the collective behavior of these quanta, not from any single one of them. This idea is deeply consistent with thermodynamics. A superfluid at equilibrium is a system in its lowest energy state, where all particles occupy the same quantum configuration. Spacetime, too, appears to exist in a state of minimal energy, the vacuum. Yet even the vacuum is not truly empty. It seethes with fluctuations, the zero-point motion of the quantum fields that fill it. These fluctuations may be the microscopic movements of the spacetime condensate itself. They are what give rise to vacuum energy, to the cosmological constant, and to the faint expansion of the universe that we attribute to dark energy. If this interpretation is correct, then dark energy is not an external force, but a property of the spacetime fluid, a manifestation of its ground state pressure. In the same way that a superfluid, helium film spreads spontaneously to cover a surface, the universe may expand because its underlying condensate naturally relaxes toward equilibrium. The acceleration of cosmic expansion, then, is not a mystery to be solved, but a natural thermodynamic behavior of a superfluid vacuum adjusting to its own quantum pressure. The analogy extends even to the birth of the universe. In the earliest moments after the Big Bang, the cosmos may have undergone a phase transition, cooling from a chaotic quantum plasma into a coherent superfluid. This transition would have set the stage for inflation, the rapid expansion that smoothed and flattened spacetime. It would also have determined the initial pattern of quantum fluctuations that later grew into galaxies and stars. The entire cosmic history could then be viewed as the cooling and flow of a quantum liquid, evolving from turbulence into order. In a superfluid, flow is quantized. It occurs in discrete steps, constrained by the coherence of the wave function. Similarly, space-time curvature may be quantized at the smallest scales. The smallest possible twist or ripple would correspond to a single unit of geometric circulation, a quantum of gravity. These discrete flows, averaged over vast distances, give rise to the continuous curvature described by Einstein. What appears to us as smooth bending is, at its foundation, a mosaic of quantized vortices moving in harmony. This interpretation resolves an ancient divide. Relativity treats spacetime as continuous, while quantum mechanics treats reality as discrete. The superfluid model unites them. A superfluid is continuous at large scales but discrete at small ones. Its macroscopic flow hides a microscopic granularity that becomes visible only under extreme conditions. The same may be true for spacetime. At human scales, it appears smooth and continuous, but near singularities, or at the Planck length, its discrete structure reveals itself, the atomic texture of reality. If gravity is the flow of a superfluid spacetime, then energy and matter are not foreign intrusions within it. They are patterns in its flow. Particles may be excitations, stable disturbances like ripples or vortices that persist within the medium. Mass, in this sense, is not a fundamental property, but an emergent one, arising from how the spacetime fluid organizes itself around certain configurations of energy. The Higgs field, which gives particles their mass, could be one aspect of this self-organization, a subtle property of the superfluid vacuum that couples to motion. Seen this way, the universe becomes a vast, self-sustaining whirlpool of information and flow. Its laws emerge naturally from the properties of the fluid that composes it. Its constants arise from the quantum stiffness and coherence of that medium. The expansion of space, the propagation of light, the attraction of gravity, all are the behaviors of a single perfect superfluid that has existed since the beginning of time. And yet, even a perfect flow can reveal complexity. Within its currents, patterns form, swirls, eddies, and waves that carry structure across scales. Galaxies spin like vortices in a boundless ocean. Black holes churn like whirlpools of infinite depth. The cosmic web itself, with its filaments and voids, resembles the interference pattern of waves on an infinite surface. The universe is not a solid sculpture, but a living sea, ever in motion, ever recombining. If gravity is truly a superfluid, then we must learn to see its behavior not only through equations, but through flow. Its ripples are its language, its vortices its memory. The cosmos is not built from rigid laws, but from patterns of motion that endure. To understand reality, we must learn to read the current, and so the next step of our journey takes us to the microscopic origins of this cosmic fluid, to the atoms of space-time themselves. There, at the Planck scale, beneath the smooth surface of the superfluid universe, lies the lattice from which geometry arises. It is in those hidden patterns, in the quantum fabric of space-time, that the deepest flow of gravity begins. At the foundation of everything we see, the galaxies, the stars, the planets, and even the emptiness between them, lies a question: what is space-time made of? To Einstein, space-time was a continuous fabric, bending smoothly around mass and energy. But quantum theory tells a different story. Nothing continuous can exist without limit. Beneath every field lies a deeper structure. Space itself, it seems, must have atoms, the smallest indivisible units of geometry, the building blocks of reality. Physicists have long sought these atoms of space-time. In loop quantum gravity, space is not smooth but granular, woven from a vast network of microscopic loops known as spin networks. Each node represents a tiny quantum of volume, each link a quantum of area. When viewed from far away, these quanta blur together, forming the illusion of a continuous space-time. But up close, near the Planck length, the universe would appear as a crystalline web of information, a quantum lattice where geometry itself flickers between existence and possibility. This vision unites relativity and quantum mechanics. Relativity describes the curvature of space-time caused by energy. Quantum theory describes discrete packets of energy and information. The spin network merges both ideas, showing that curvature is not imposed on space, but emerges from the collective behavior of its quantum building blocks. Just as fluid motion arises from molecules moving together, the smooth flow of gravity arises from countless microscopic quantum interactions. Einstein's equations in this light are the hydrodynamic limit of a deeper quantum fluid. In this framework, space is not a passive arena, but a dynamic system of relationships. Geometry itself becomes an expression of entanglement, a record of how the fundamental quanta of space-time are connected. The closer two regions are entangled, the shorter the distance between them. The weaker their entanglement, the farther apart they appear. Thus, distance is not a physical separation, but a measure of correlation. The universe is not built from points, but from relationships, from the threads of information that tie everything together. At the Planck scale, time also dissolves into discreteness. Each moment becomes a quantum transition between different configurations of the space-time network. Reality ticks not in seconds, but in fundamental units of change, the rearrangement of information between the quanta of geometry. From our macroscopic perspective, this dance appears as the smooth flow of time. But beneath it lies a discrete rhythm, the heartbeat of the universe, pulsing every 10 to the power of -43 seconds. Black holes provide our best clues about these microscopic structures. Their entropy, the amount of information they contain, scales with the area of their horizons, not their volume. This implies that the fundamental bits of space-time reside on surfaces, not in bulk. The smallest unit of area, roughly the size of the Planck square, may correspond to a single quantum of information, a pixel in the universe's geometric code. When a black hole evaporates, it releases these bits gradually, preserving the total information. The process reveals that space-time is not continuous, but digital at its core. The same principle governs the entire cosmos. The smooth geometry we inhabit is the collective behavior of an unimaginably dense quantum network. Every ripple of gravity, every ray of light, every motion of matter is an emergent pattern in that network's flow. The universe computes itself through these interactions, evolving according to the conservation of information. Matter and energy are simply stable configurations of this information, localized distortions in the quantum geometry. This realization transforms our view of existence. We are not observers floating within space. We are excitations of space itself. Our atoms, our thoughts, our lives are patterns in the quantum lattice of the cosmos. When we move, it is space-time that moves within itself. When we think, it is space-time processing information. Reality, in this sense, is a vast quantum computation unfolding without end. And yet, even this quantum fabric must have texture, not always smooth, sometimes chaotic. The next step leads us into that turbulence, where the perfect symmetry of space-time breaks into swirling vortices, where gravity behaves like a living current, and where the flow of the universe reveals its deepest motion. At its deepest level, the universe behaves like a fluid, not made of matter or energy, but of pure quantum fields. These fields are restless, even in their quietest state, flickering with fluctuations that never entirely vanish. To call this vacuum is misleading. It is not emptiness, but fullness, a dense sea of potential, alive with motion. And this motion is governed by the same laws that describe the flow of superfluids and waves in the quantum world. The cosmos, in its most fundamental form, is an ocean of hydrodynamic behavior, rippling with the pulse of creation. Quantum hydrodynamics studies how fluids behave when quantum effects dominate. At ordinary scales, fluids are chaotic and dissipative, but when cooled near absolute zero, quantum order emerges. Every particle moves in perfect synchrony, forming waves that flow without friction. These systems, Bose-Einstein condensates, superfluid helium, and superconductors, show us what happens when the collective motion of matter becomes coherent. The entire fluid behaves as one organism, a single wave function. Now imagine that the vacuum itself behaves this way. The energy of empty space, what we call vacuum energy, acts like quantum pressure within a superfluid. This pressure pushes outward, expanding the universe. The phenomenon we describe as dark energy may not be a mysterious force, but the natural hydrodynamic behavior of this cosmic quantum fluid. Just as waves in water travel according to its pressure and density, the expansion of the cosmos reflects the flow of energy through the quantum vacuum. In this view, gravitational waves are ripples in the density of that superfluid. When massive objects move or collide, they disturb the fluid, creating waves that travel at the universal speed of light. Because the fluid is perfectly coherent, these waves can cross the universe without scattering or fading. They are pure, lossless vibrations, the hydrodynamic sound of space-time itself. The mathematics of these waves mirrors that of ordinary fluids. The Einstein equations describe how energy and pressure determine curvature, just as the Navier-Stokes equations describe how density and velocity determine flow. The difference is scale. In fluids, the medium is made of atoms and molecules. In space-time, the medium is made of quantum information. Both obey continuity, conservation, and equilibrium, the three fundamental laws of hydrodynamics. Gravity, in this sense, is not an independent force, but the large-scale behavior of a cosmic fluid in motion. This fluid-like behavior is clearest near extreme conditions. Around a rotating black hole, space-time drags nearby regions with it, creating a whirlpool of geometry. This frame-dragging effect is the gravitational equivalent of a vortex in a superfluid, a region where the flow circulates endlessly around a core. The faster the rotation, the deeper the vortex. If space-time truly behaves as a quantum fluid, then these black holes are its vortices, stable and eternal patterns of flow. Even the expansion of the universe itself resembles fluid motion. In hydrodynamics, a low-pressure region draws fluid outward until balance is restored. In cosmology, the vacuum pressure of dark energy does the same, stretching space to reduce its energy density. The galaxies are not flying through a pre-existing void. The void itself is expanding, carried by the pressure of the quantum fluid that fills it. The cosmic expansion is not a movement through space, it is the movement of space. There are also hints that turbulence exists within this flow. In a superfluid, when motion becomes intense, vortices interact and tangle, producing a form of quantum turbulence. The early universe, during its first moments, may have undergone such a turbulent phase. The rapid fluctuations of quantum energy could have seeded the irregularities that later grew into galaxies and clusters. The ripples we observe in the cosmic microwave background might be the fossil remains of that primeval turbulence, the fingerprints of a hydrodynamic storm that once filled the entire universe. At smaller scales, this quantum hydrodynamics continues in silence. The vacuum energy does not rest. It continually exchanges virtual particles that appear and disappear, maintaining the balance of the cosmic fluid. This invisible motion sustains the stability of space-time, ensuring that geometry remains coherent even as energy and matter flow within it. Without this constant microscopic activity, the universe would freeze into stillness, losing its ability to evolve. The analogy to a superfluid also explains why the universe resists friction. In a normal fluid, flow generates heat because microscopic collisions destroy coherence. But in a superfluid, coherence is perfect. The waves reinforce each other rather than cancel. That is why gravitational waves propagate endlessly. They are the undisturbed motion of a fluid with zero viscosity. This perfection is not a coincidence. It is the natural state of the quantum vacuum, where the laws of physics reach equilibrium. If we could look deep enough beneath atoms, beneath particles, beneath fields, we might see the universe's foundation not as fabric, but as flow. The geometry of space would shimmer with waves of information. The motion of time would be the current of that flow, and gravity would be the whisper of its motion. Everything would be in motion, yet nothing would be lost. The cosmos would appear not as a structure, but as a song, a continuous vibration of quantum hydrodynamics unfolding through eternity. In this perspective, existence itself becomes a kind of fluid dynamics, not of matter, but of being. The equations of physics are the grammar of its motion. The constants of nature are the rhythm of its waves. And we, as observers, are small eddies within that infinite current, momentary patterns in the superfluid sea that is reality. But no sea, however, smooth, is free from turbulence. Even in perfection, there is motion that breaks symmetry, swirls that create chaos from calm. If space-time flows, then it must sometimes twist, curl, and collide with itself. To understand gravity fully, we must explore those turbulent regions, where the flow of space-time becomes wild, where black holes merge, where the quantum sea froths and foams. There, in the storms of the cosmic ocean, we may find the deepest truth of all, that even chaos has order, and that the universe flows through both as one. Space-time is often imagined as serene, an infinite calm stretching between stars. Yet beneath that stillness, the universe stirs. Gravity, like all fluids, can flow smoothly, or it can whirl into turbulence. When the quiet symmetry of space-time breaks, when energy concentrates and motion collides, the geometry of the cosmos twists upon itself. Black holes spin, galaxies rotate, and gravitational waves ripple outward, all signs that the fabric of the universe behaves like a fluid caught in motion. Near a rotating black hole, this truth becomes visible. The intense spin of such an object drags space-time around it, forcing everything nearby to rotate. This phenomenon, known as frame dragging, is the gravitational equivalent of a vortex in a superfluid. Nothing can remain still. All motion is caught in the swirl. Even light itself is drawn into circular paths around the vortex. The equations describing this region, the Kerr metric, reveal that space-time behaves not as a rigid geometry, but as a fluid with rotation, circulation, and flow. When two black holes merge, the turbulence becomes cosmic. The immense distortions in curvature produce waves that travel across billions of light years. These gravitational waves are not separate from space-time. They are space-time in motion. Each wave carries energy and information, spreading outward like pressure waves in a fluid. The detectors that have recorded these signals are hearing the hydrodynamic heartbeat of the universe, the vibration of the space-time ocean. Turbulence, in this context, is not chaos without law. It is complexity emerging from simplicity. In ordinary fluids, turbulence occurs when flow becomes unstable, when velocity and pressure fluctuate too rapidly for the medium to remain smooth. In the space-time fluid, similar instabilities may exist. When gravitational fields interact, when matter collapses or merges, the flow of curvature becomes non-linear. Vortices twist and reconnect. Energy cascades from large scales to small, creating a hierarchy of motion that could extend all the way down to the Planck length. At that smallest scale, space-time may foam, a term coined by John Wheeler to describe the fluctuating geometry of the quantum world. There, the distinction between space and time becomes uncertain. Tiny wormholes may appear and vanish. Microscopic vortices of geometry may twist briefly before dissolving. This is quantum turbulence, the storm beneath reality. It is invisible to us, yet it determines everything we see. The smoothness of large-scale spacetime arises only because the microscopic chaos averages out, just as a calm ocean hides the constant motion of molecules within it. Even the large-scale structure of the universe may bear the marks of turbulence. The cosmic web, that vast network of filaments and voids stretching across billions of light years, resembles the patterns created by fluid turbulence. The distribution of galaxies mirrors the eddies of a flow that has evolved for 13 billion years. Gravity acts as the medium, matter as its dye, revealing the hidden currents that shape the cosmos. The spiral arms of galaxies, the jets of quasars, the collision of clusters, all are manifestations of vortices in the great gravitational sea. The mathematics of this flow connects seamlessly to fluid dynamics. The Einstein field equations, when expressed in the right form, resemble the equations governing incompressible fluids. They describe how energy density, pressure, and velocity fields interact to produce curvature. Solutions like the Kerr and Schwarzschild metrics are not static objects but flow patterns, steady states of the space-time fluid. When these flows become unstable, they give rise to gravitational turbulence. This turbulence may also play a role in cosmic evolution. In the early universe, as energy densities reached unimaginable levels, space-time itself could have undergone a turbulent phase. Waves of curvature would have cascaded and interacted, producing fluctuations in density that later seeded galaxies. Even now, during black hole mergers or neutron-star collisions, the universe may experience bursts of this hydrodynamic chaos. Each event stirs the space-time ocean, sending ripples that carry the memory of that motion across eternity. There is beauty in this turbulence. It reveals that even the most violent motions of the universe follow patterns of order. Fluid turbulence on Earth creates fractal structures, vortices within vortices, endlessly nested. The same may be true of space-time. The geometry could organize itself into self-similar structures, with large-scale vortices echoing the motion of smaller ones. Gravity, therefore, is not random, but patterned, a choreography of swirling energy connecting scales from the subatomic to the cosmic. The energy carried by these gravitational waves is immense, yet perfectly conserved. Unlike sound or light in ordinary media, they lose no power as they travel. This lossless transmission is a hallmark of the superfluid nature of space-time. Even its turbulence, however chaotic, never destroys energy. It merely redistributes it, transforming one form of motion into another. The universe, through its vortices and ripples, remains perfectly efficient. If we could visualize this process, if we could see space-time itself, we would witness something like a boundless ocean of light and shadow. Great waves of curvature would surge and fade. Vortices would spin and merge. Filaments would stretch across the deep. Each black hole would be a whirlpool. Each galaxy a slow spiral of flow. Each gravitational wave a shimmering pulse of the medium itself. The cosmos would not appear still or empty, but alive, breathing in cycles of motion and rest. This vision challenges our traditional understanding of time. In a turbulent fluid, motion never truly repeats. Patterns form and dissolve, never returning exactly to their previous state. Time, therefore, in such a universe, is not a line but a flow, a constant reorganization of structure. The universe does not tick like a clock. It moves like a river, always the same yet never identical. The arrow of time is the direction of that flow, shaped by the deep turbulence of space-time itself. In the end, turbulence may not be a flaw in the cosmic design, but its essence. Without instability, there would be no evolution, no stars, no life. The swirling motion of gravity gives birth to structure, complexity, and awareness. We exist because the universe flows, because its equilibrium is never perfect, because its fluid geometry allows motion and change. And as this current continues to move, it reminds us that we are part of it. Fleeting vortices in a boundless sea, born of turbulence, sustained by flow, destined to dissolve back into the calm from which we came. The universe flows through us, and we through it. Gravity does not pull us downward. It carries us forward, through the ever-changing current of space-time. From the first light of creation to the last whisper of fading stars, the universe has been in motion. Nothing in it rests. Galaxies drift, stars orbit, and even the silent void hums with fluctuations that never cease. To live within this motion is to inhabit a river, an unending current of energy, information, and geometry that we call space-time. Gravity is not separate from this flow. It is the flow, the movement of the universe within itself, the rhythm by which existence remembers its own unfolding. Einstein showed that gravity is the curvature of space-time, a bending of geometry caused by energy. But the deeper we look, the more that curvature behaves like motion, like a fluid streaming around mass and returning to equilibrium. Quantum theory reveals that this flow is not smooth, but made of countless interactions, each carrying information. Together they create the illusion of continuous geometry. What we call reality is the average motion of an invisible ocean, one whose waves are too small and too fast to see. This ocean never stops flowing. Every star, every planet, every human being moves within it, guided by the gentle currents of gravity. When an apple falls from a tree, it is not being pulled downward. It is following the easiest path through the space-time stream that Earth creates. When the moon circles our planet, when light bends around a galaxy, when black holes spiral together, all are movements of the same current. Gravity does not act, it flows. In this flowing universe, energy, information, and geometry are one. A change in one changes the others. When matter moves, information redistributes. When information flows, space-time bends. When space-time bends, energy shifts. This feedback never ends. The cosmos sustains itself through the continuous circulation of these three elements, like a perfect superfluid with no friction and no loss. Its total energy remains constant, yet its patterns evolve endlessly. Seen this way, gravity becomes the great equalizer, the universe's way of preserving balance. Every concentration of energy is matched by a corresponding curvature of space. Every flow of information is balanced by the expansion or contraction of geometry. The result is a self-regulating system that needs no outside guidance. The universe is its own equilibrium, always adjusting, always flowing, always returning to harmony through motion. The river beneath reality reveals itself most clearly in black holes. These are not voids of destruction, but vortices in the cosmic current. Spacetime twists around them, creating stable whirlpools of information. Their event horizons are the surfaces of perfect flow, where time slows almost to stillness and space folds into itself. Even when they merge, they do so with elegance, releasing gravitational waves that ripple outward like rings in water. These waves carry the memory of motion, the echo of the river itself. Every gravitational wave that passes through Earth, every signal we detect, is the song of the universe's movement. It is space-time speaking in its native language, vibration. These waves travel without resistance, crossing billions of light years unchanged. They are the proof that the cosmic current is real and that it flows with absolute perfection. The universe does not waste energy, it transforms it. It does not lose information, it redistributes it. This flow extends beyond matter and energy. Time itself may be a property of the current. Each moment is not a separate frame, but a change in the river's pattern. The past is the direction from which the flow has come. The future is the path it continues to carve. We drift along it, not as observers but as participants, waves in the same stream, patterns that rise and fade but never truly vanish. The flow of time and the flow of gravity are one and the same. If we could step outside the universe and look down upon it, we would not see empty space or scattered galaxies. We would see an ocean of motion, vast currents of curvature and light, spiraling and colliding in endless harmony. The galaxies would be eddies, the black holes would be whirlpools, the gravitational waves would be shimmering ripples on the surface. From that vantage, the cosmos would appear alive, a living sea of energy and information, constantly reshaping itself, yet always whole. Even consciousness belongs to this motion. Every thought, every spark of awareness, is a flow of information through a biological structure. The neurons of the brain, the particles of the body, the atoms of the air, all move with the same current that guides stars and galaxies. To be conscious is to be part of the river that knows itself. We are not standing beside the flow of the universe. We are that flow, momentarily organized into perception. When we die, the pattern dissolves, but the current continues. The atoms return to the stream. The information is redistributed. Nothing is lost. The universe does not end. It recomposes itself. Every atom in our bodies was once part of a star, and every photon that warms us will one day drift into the cosmic sea. We are temporary shapes in an eternal motion. In the end, gravity is not a pull, not a force, not a constraint. It is the gentle movement of space-time seeking balance. It is the continuity that allows stars to form, orbits to hold, and time to pass. It is the great current that sustains all things, binding the smallest particle to the farthest galaxy in a single, unbroken flow. To exist is to drift within this current. Every orbit, every fall, every wave of light is part of the same motion, the cosmic river that runs beneath all forms. We do not stand on the shore of this river. We are suspended in it. We move because it moves. We exist because it flows.